and officially started 2 days ago, Monday. So the beam runs until 8:38, and then you can see when the beam was green, it was on, and then finally APS came to an end and started a new era. So I will squeeze my talk for 10 minutes. And this is the message I want you to have from a user point of view. What does that mean, APS-U to you? And what we can expect, and what we can dream of, and what you can contribute. Before I start my talk, I want to show you, and this is an annual meeting for 2 weeks. And there are 3 days of a workshop relative to our group. So one is today, this morning, nuclear resonance, and tomorrow there will be for the Helix phonon part. And then on Friday morning, there's a RIGS part. So if you have time, if you are interested, please join in. So what does the APS-U mean to us? What is the APS now? Right now, the APS is 7 GeV, 100 milliamp, as you know, and so far it has been the brightest the light source in the United States, and with a small beam coherence, and very importantly, it has a very unique timing structure. So it's suitable for time-resolved experiment, especially for nuclear resonance scattering at sector 3. And these are the basic facts. And the most importantly is the APS beam structure. It's very unique among the several major beamline, major storage array in the world. So about 60%, 63% of 24 bunch mode, and give us a very suitable timing structure for nuclear resonance. And another 16% hybrid mode we can use, and about 20% of the 324 bunch mode, which we cannot use for the nuclear resonance scattering. 3ID is one of the pioneer of a very early beamline at APS. So we are the beamline. The author is here, Brent, and Tom, Tom and Ergin are here. So we are the first beamline to see the X-ray, and also the first paper published in 1997 among the APS all 20 some years publications. So what is the APS-U? You have heard a lot, and for the last 2 days, if you participate in the user meeting, you already heard lots of these. So this is about $800 million investment from the DOE, and we are using the existing terminal infrastructure. And the investment even is split between beamline and accelerator. So the accelerator will be a brand new facility, but the beamline is not, every beamline will be new. So some of the beamline, like the feature beamline in the green, will be new, but the other beamline is enhanced beamline. So for sector 3, 30, and 27, we are in the enhancement beamline. So the new ring will have better emittance and better coherence for after the upgrades. And the result is brightness will be 500 times or 2-3 orders better after the upgrades. And this is the fact is there was some delay according to the plan from last year. So the official ending date of the APS is last the Monday, April 17th. So the coming back date is April next year. So in about a year, we will finish the construction and bring back, of course, the beamline will need some commission time, depending on if it is new or existing. So it's a little bit different. So of course, because the beam becomes smaller, so the brightness of the synchrotron becomes So 2 orders are better if you can make use of these features. So basically, what is in the pipeline of upgrade is you have almost 2 orders of emittance improvement. And but of course, the price you pay is from 7 GeV to 6 GeV. You have less flux if naturally, but with optimized angulator and also the current is doubled. So at some beamline, at some program, you have some gain on the flux too. But the main gain is on the brightness. You have several order, 2 orders of brightness gain. So, and of course, associated with the upgrade, you have better optics and better detectors. So you can make a gain of this. So so before the upgrade, you have such kind of shape of the beam, and after the upgrade, you have a point source from the electron beam. And so what already available for us is we have enhancement project supported by the APS-U at sector 3. We have already got this focusing KV mirror, which was mounted last month and already commissioned last month and already available after the dark period, after the APS-U becomes back again. So we can expect the enhancement of focusing capability of sector 3. So, but there are some challenges, and because as you know, for our measurement, always the concern is a flux, and how good the flux we can gain, and how good the experiment we can expect. The flux wise, this is green is 7 GeV is the current situation or the past situation, and the red one is 6 GeV, 200 milliamp. You can see at 14 kV, it's about the double the flux. But the heat load of the angulator is different because the green one, the dotted green one is the first harmonic, but in the future, the red one is covered by the third harmonic. And with optimized angulator gap, so for example, the red one in here is 80 millimeter device, and then you can see some more gain for if we use this 80 millimeter for to generate 14 kV photons, you get even more another double factors can be expected from at 14 kV. And in order to cover the 20 to 30 kV, you have to have another, because the red curve doesn't cover this range, 20, 30 kV. You have to have another angulate to make the European dispersing program continue. So this is what we are pursuing, and this is called revolver angulator. And for the left is a traditional revolver, and the new one is the new invention of the APS insertion device group. So we are trying to get this one. We are still in the process of pursuing this. So basically using 18 millimeter to generate for 14 kV and 25 millimeter to swap these two, and then you revolver angulator to cover the higher energy of the nuclear resonance program. So another thing we can expect, this is a new in vacuum cryogenically cooled sub-millieV high resolution mono. And with this one, you can expect a greater improvement of thermal stability in the vacuum. And also it's better than the millieV resolution. And it give you a 1 micron beam size at 14 keV. But this is a little bit long run. It's not be funded, and this is something we want to pursue. Another big challenge is the beam structures. So far I have shown you this is APS so far. It's very favorite for the nuclear resonance program. In the future, after APS-U, And this is the bunch structure we are talking about. Two kinds of structure. One is 324 bunch mode. Probably this will become the main, especially at the beginning of the running. And instead of 24 bunch mode, we are talking about 48 bunch mode, which is make our iron 57 program difficult. So to summarize this one, this is APS running mode, and this is APS-U running mode 36 instead of 153 nanosecond. When we deal with different isotope, different resonance, you can see for different isotopes, this is iron, long lifetime we call, and this is European dysprosium tin and some others, short lifetime isotopes. And for inelastic scattering, with the 48 bunch mode, we have some gain. We don't lose after the APS-U. And for the Mosbar and for the short lifetime, it doesn't affect 76 nanosecond. It's just okay. For iron 57, it will suffer, and majority of the Mosbar type of iron 57 will will suffer. So from this drawing, we can, the information that we want to deliver is 48 bunch mode is essential for the nuclear resonance program to continue. So inelastic program and also short life Mosbar will depend on this running mode. So there is another thing we want to do is we want to develop the energy domain Mosbar to make use of 324 bunch mode. So there are several ways. This is our timing mode so far. It has been very successful for the last 25 years. And now we had this using the hybrid mode, and Tom has this fast shutter scheme to make use of energy domain measurement. And we have several. We have one way is using iron borate to apply for the energy domain, and which has been used at the ESRF Petrol 3 and Spring 8. And we have this unique approach, and this is under development. We are using polarizer scheme to filter out the prompt, and then based on that, we are developing this energy domain spectroscopy, and the details will be followed by Tom's talk, and will be available after the dark period for the 3D users. And this is something simulate and for the energy domain busbar spectrum using the polarizer scheme, and Tom can show you a little bit more. So this is the summary, and the information, the message I want you to know is we have exciting upgrades already started of APS, and from sector 3 we have lots of things going on. And already we have a small size capability, and we are asking more firm commitment of the 48 bunch mode to continue our program. And we have a new spectroscopy spectrometer working, and will be delivered after the dark period, available for the user community. And we have lots of things to do, and at some point we need your help. And if you have good idea to be involved, please let us know. And thank you very much.
All right, thanks, Jill. So at the end of this workshop, so we'll have a session for more discussions. But if anyone has a quick question, you can just unmute yourself and then ask, and then please identify yourself, name, institution, like that. If not, since we're pressed for time, let's hear from Tom, who is a beamline scientist at AXS Group, and work across all 3 sectors actually and all APS. So Tom, please start. Can you share? All right.
Can you see it?
Yes, but not in the presenter mode. Good. No. Yeah.
All right. So I'll be talking about the Mossbauer microbeam and changes that will be coming after the upgrade to how we do these measurements for iron-based samples. So just an outline. So I'll give a brief overview, very brief, of how we do it currently. And then the changes that will be coming from the upgrade that impact the nuclear resonance scattering. And then I will introduce this a different approach to doing iron-based Mossbauer spectroscopy, where we take energy absorption spectra instead of taking time spectrum. And then a test setup that I put together just last November, took some measurements, and I will share those results with you. So the way we do it currently is we do it in a time domain up till now, with the small exception that the fast shuttle spectrometer can do both time domain and energy domain. Almost all of our Mossbauer spectra are taken in the time domain. This involves an X-ray flash that excites all the nuclear transitions in a sample, allows them to interfere, and then the manner in which they decay is reflected in the time response. And from that, one can extract the hyperfine interactions in the sample. So the minimum requirements you need to do these sort of measurements are, you need an adequate amount of dark time between the pulses. By adequate, I mean the time should be basically a nuclear lifetime, but preferably longer. And then you need a method to suppress the X-ray flash, and then you need fast single photon detector and detection system to carry out the timing to construct a time spectrum. So the two ways we currently do it, or have up until now done it at sector 3, one is in 24 bunch mode. We use a high resolution monochromator. This is by bandwidth reduction. We reduce the intensity of the X-ray flash, and then time gate out the prompt flash, as well as introduce an absorber to get additional suppression as needed. With this 153 nanosecond dark time available in 24 bunch mode, we end up with a time window that's about roughly 120 nanoseconds. If you go to hybrid operating mode, the difference is that we suppress the flash using mechanical shutter. This is a shutter that is closed to protect the detector from the flash, and then it opens quickly after the flash has arrived, so that the detector can see the nuclear resonant scattering coming off the sample. In hybrid mode, we have the advantage of a much longer time window, and so one can get much more precise information due to the longer time window. So the changes that are coming, as Jiyoung alluded to, is that the low emittance electron beam, the immediate impact is a reduced horizontal X-ray source size. What this translates to is that one can focus the full beam to 1 micron with high efficiency. So we have new mirrors for this, so that we've tested it out already, so that will work well after the upgrade. There's also higher X-ray power density on wide beam components, but I will not address that here. And then the timing modes, as Jiyoung also mentioned, the prior timing modes were 24 bunch mode, hybrid mode, and 324 bunch mode. Those are going to be replaced with just 324 bunch mode and the new 48 bunch mode. The 48 bunch mode is 76 nanosecond dark time. This is less than the nuclear lifetime for iron-57, which is 141 nanoseconds. And so it's getting to be a bit of an issue for us. So the impact, so the isotopes, if you break them up into short-lived resonances as well as the long-lived resonances, the short-lived resonances shouldn't have any problem with the reduced dark time between pulses in 48 bunch mode. for both NRIX, the phonon measurements that is, as well as Moss bar spectroscopy. I put an asterisk there because there are some caveats to that. There are some listed at the bottom here. I have 3 caveats. One is associated with bunch purity, which is simply not known. In fact, all 3 of these are known unknowns, if you will. As long as those issues are not a problem for us, then there will be no problem with the short-lived resonances. And they will continue in the same way. We'll continue to do time domain measurements and measuring time spectra at 10 europium and dysprosium. For the longer-lived isotopes, which is essentially iron only, we don't really do krypton anymore. The isotopes, this isotope has a lifetime of 141 nanoseconds, as I mentioned. For the NRIX, there shouldn't be any impact, but again, the same caveats apply. So as long as the bunch purity is not a problem and the 48 bunch mode remains as planned and is not being altered, there's some chatter that it may be changed, but let's just assume for the moment that it stays the same, and there shouldn't be any impact. The Moss bar spectroscopy, though, will have a direct impact. The 76 nanosecond dark time, once you subtract out time loss because of the timing electronics and potential bunch purity issues, that 76 nanoseconds could easily be cut in half down to something like 30, 40 nanosecond time window, which is mostly unacceptable for almost all iron-based Moss bar spectroscopy measurements. So we'll introduce a new energy domain approach to accommodate and allow that program to continue. So this is just a conceptual sort of block diagram. So we use the synchrotron radiation to drive a gamma ray emitter, and at the same time, this assembly here will suppress the background, and so the output will simply be a spectral shape of gamma ray lines, and I will show what that looks like in following slides. Then we will focus the beam down to 1 micron. You put your sample there, and then there's a detector, and it's all pretty straightforward. And then a data acquisition is identical to what is used in a traditional Moss bar setup, where the velocity is correlated with the arrival of the photons in the detector, and one can construct an energy spectrum. And the energy sweeping is done by Doppler shifting the emitter. So this is based on some previous work I did 10 years ago. The approach is going to be based on that. So we use cross polarization filters. We put them, or by cross, I mean they're orthogonal. So we have a sigma polarized polarization filter and a pi polarization filter. And then in between them, we put a resonant material. This is a material that is optically active within a resonant band. And so the cross polarization filter suppresses all the non-resonant radiation. And the nuclear resonant material introduces some polarization switching just in the resonant bandwidth. And so one can get a spectrum that is just of gamma rays out with some small background. So I did this, trying to generate a single line, and I used 2 different methods. One, just a magnetic interaction using stainless steel placed between cross polarization filters. Then I applied a small magnetic field. The stainless steel grade was a non-magnetic grade of stainless steel. But if you apply a small external magnetic field, you can introduce some partial splitting, and this allowed me to introduce some polarization flipping and generate a single line. So the spectrum on the upper right-hand corner is a measurement of another stainless steel foil as the sample. So the emitter is a stainless steel and the sample is a stainless steel, and I could scan one against the other and generate that Moss bar absorption spectrum. The second approach used a combination of magnetic and electric interaction. And here I chose a potassium ferricyanide. This is a single crystal. It's a water-soluble salt, so it was something I could easily make in the lab. And it was unenriched crystals, but I picked the principal axis of the electric field gradient, and I make it coaxial with the magnetic field. And I place that in between the cross-polarization filters, and that allows me to generate a single line. That was a very sharp line, but same as stainless steel, the counting rates were low. So in both cases, the counting rates were low. And this was just a general problem with trying to generate a high quality single line. Counting rates are just low. So the approach we will adopt is to use a multi-line source. that has much higher counting rates, but is also easy to know, easy to measure, and it's very stable over long periods of time. So it should be a very reliable instrument as a result. So here we take a magnetized iron foil placed between cross-polarization filters, and it's arranged in such a way that we excite all 6 resonances. The net result is you get a combination of sigma and pi polarized radiation that is resonant in between the polarization filters. All the sigma components are suppressed at the pi polarization filter, and you just get the resonant pi radiation out. So the output beam of this instrument will be pi polarized 4-line spectrum, as you see there. So, and this iron foil or iron film is mounted on a velocity transducer, and it oscillates back and forth, and that's what allows us to sweep the energy in measure an absorption spectrum. So after we generate that 4-line source, we then have the focusing. This relies on low emittance of the storage ring, as I mentioned, but we have a new KB mirror that allows us to get down to 1 or 2 microns. And the polarization optics preserves X-ray beam emittance, and so we won't have any disruption and should have no problem getting down to 1 micron. The sample environment, I just wanted to make a note of some changes in the sample environment in terms of what needs to pay attention to. The absorption losses around the sample environment are quite critical, and any of those should be minimized to a great extent. That wasn't an issue in timing domain because we were already using an absorber, and one could simply remove some absorber to compensate for any additional losses that one might have around the sample. That's not the case in the energy domain. So in the case of high pressure measurements using a DAC, one should use diamonds that are milled off on the backside. Sometimes they're called perforated diamonds. And also the sample should be mounted on low absorbing mounts. Another issue is the sample vibration. So because the energy spectrum is based on Doppler shifting of the emitter relative to the sample needs to be stationary. And so vibrations can ruin the energy spectrum. So if you're using a low cryostat, it needs to be a low vibration one to allow for that. And also samples need to be mounted to the stages more securely so that there is no motion. Motion along the beam is the motion that matters. The detector will be changed. We will not use an avalanche photodiode as you're normally used to, but we'll be using a high efficiency single photon detector when we're doing in transmission geometry. So this is typically a sodium iodide crystal mounted on a photomultiplier tube. The option to do SEMS is there. So SEMS refers to conversion electron loss bar spectroscopy. This is basically a surface sensitive approach where one looks at just the electrons produced from the conversion process off the sample, and so it restricts your measurement to just the sort of the top roughly 100 nanometer layer of material. But we don't currently have any plans. But if anyone is interested in that, please let me know, and we can consider trying to put that together. So here's a measurement of the test setup. I used some existing polarization filters. One of them was low efficiency. The other one was a recent modification that I introduced a couple of years ago. And then the emitter was just a unenriched iron foil mounted on a velocity drive with a small magnetic field so that it was magnetized. And I did this to assess the counting rates and issues and all the things that I could do to improve it. And the spot size here in this case was just 20 microns. So the measurement on the right is of a 2 micron enriched iron foil. And it's not your typical 6-line spectrum, but the sample, of course, is a 6-line spectrum. But when you convolve it with the emitter spectrum, this is what you get. And Wolfgang has modified the CONUS software package to accommodate these measurements. So one can introduce the source spectrum, and one can fit energy spectra in this way. This measurement was 7 hours. That sounds egregious because this is like the best sample you can do, but the newer instrument will have significantly higher, significantly higher data rate. So the collection time will be a factor of 60 smaller than this. So one can expect this spectrum from this sample with this level of data quality to be collected in about 7 minutes with the new spectrum after the upgrade. Yeah. So I wanted to characterize the emitter more carefully to assess some things. And so I used the fast shutter spectrometer to do that. And so this is just showing the spectrometer with the magnetized emitter located between the shutters so that I could carry out the measurement. And this is the result of that measurement. I took a long time window time spectrum in hybrid mode, so I could measure easily out to 900 nanoseconds. And the red line is the fit of the data using condensed software. From this measurement, I could determine all the nuclear hyperfine parameters so that I could reconstruct the energy spectrum of the emitter. And when I introduce the polarization filtering as well, I get the 6-line spectrum here that we see. One of the things I learned in this approach from this measurement is that there's a slight discrepancy here in after 400 nanoseconds. This is due to an incomplete magnetization of the film. And so the magnet that I had built for this purpose needs to be a stronger magnet in the future. And so that will be taken care of. So some test measurements. I measured some enriched samples here. These are stainless steel on the left-hand side. It's the 2-micron enriched stainless steel. This collection time was about 6 hours. Again, so the new spectrum the data rate will be 60 times faster. So this is the kind of spectrum you would expect from this enriched stainless steel in about 6 minutes of time. I didn't have time to fit the data yet. The other sample was done by Jennifer Jackson. This is a clinopherricillite, and she fit this data as well. So she fit this quickly with a 2-site model and got pretty good results using the new software package. We also measured some unenriched samples. These are amphibole single crystals provided by Bob C. Rashbacher. The one on the left is from an amphibole single crystal from Mount St. Helens. And here we measured, these samples have very little iron in them. And of course, they're unenriched. So the collection times are significantly longer. We measured this for 11 hours, and you see the data quality isn't as good as the previous spectra on the previous slide. But this is the kind of spectrum you can expect in about 11 minutes. And obviously, you would want to collect on this sample for many hours. So, you know, if I extrapolate this and I say I want a quality of 9 sigma, I should tell you what I mean by that. The quality is just the magnitude of the dip in relation to the magnitude of this dip, say, in relation to the RMS of the baseline. And so typically you want that dip to be 50 RMS of the baseline. More obviously is better if you have the time, and you know that's always a trade-off one has to make. So if you wanted to do that, you would end up measuring the sample about 5 hours, and then you would have a dip that was about 50 sigma. You of course could count longer if you wanted to get even higher quality fit. The other amphibole is from the Long Valley caldera out in California. And we measured that for almost a day. This is a very low iron concentration, 3.5% effect here. 3.5% effect, that's the magnitude of the dip to the baseline. So in case you're wondering what that means, that's so, yeah. And again, the quality is about the same, measured in 21 hours. And so this is what you would expect in about 21 minutes with the new instrument. And so I just have some sum up here. So the multi-line spectral shape of the emitter is very stable and very well known and produces very high counting rates. And so we're confident that this is the best approach available to us. The new instrument will introduce a 1-micron focusing. So we'll do Moss power microbeam with a much smaller spot size. And the Kona software has already been modified to handle this kind of data. And but I can make the source spectrum available to anyone else who would like to incorporate this kind of fitting into any other software. And I just want to acknowledge some people that helped out, Rick for machining a lot of parts. As always, Jennifer for her samples, as well as for showing up to the beam time and helping out with doing some of the measurements, as well as fitting her spectra. Bobsy for her amphibole crystals, and Wolfgang for modifying his software package. Jiyoung and Emily for beam time support, and Joseph and Mafe for their magnet help. So that's all I have. Thank you.
All right, thanks, Tom. Any quick questions? We have 2 minutes the time. So, okay, Dongzhou.
Hi, Tom. Can you hear me?
Yes.
Yes.
Yeah. Thanks for a very nice talk. So I do have a question. So does this mean that if I want to do, for example, laser heated diamond cell experiment with MOSFET, is that still possible?
Is it still possible? Yeah, it should be possible.
But the sample is moving, right? The sample is moving.
Sample is moving. Yeah. You wouldn't do it with energy domain. So it depends on exactly what you mean by, I mean, the laser heating, of course, you can still do. As far as doing Mossbauer spectroscopy, you could take a time spectrum with a limited time window. If all you want to do is get the integrated counts.
Okay, thanks.
Yeah. Is that it?
Other questions, comments? Okay, all right. All right, so let's move on. So for the next 2 talks, we have our colleagues from Europe. Thanks for working in your evenings. So first we have Professor Matthew Roskos. He's from Institute of Mineralogy, Physics of Materials, and then Cosmochemistry. Also at the National Museum of Natural History in Paris. He's currently the deputy director there also. So Matthew, take over, please.
Okay, thank you. So do you see the slides?
Yes.
Okay.
But not in the presenter mode yet?
Yeah, I'll try to. I hate Zoom. It's coming, hopefully.
It's a little button at the bottom. Yeah.
Is that okay?
Now it's good.
Okay, so good morning, everybody. For me, it's pretty late in the afternoon. I will show you the results of what we've been doing for several years now, to be able to analyze the samples brought back by the Japanese mission. The name of the mission is Hayabusa 2, and it was supposed to bring some samples back from the asteroid Ryugu. Of course, as you know, the samples came back during the COVID pandemic, and so this is pretty much the experimental setup. So as you can see, we were somewhere in France with my colleagues Pierre and Gisée, and all the sample handling has been made by Barbara, Jiyoung, Michael, and Erchan. So it was very, very frustrating for us since we spent years to convince Japanese JAXA to give us some samples, but actually the samples never went to France at this time, at least the first samples. So it was really frustrating. So why was this mission designed? So there were several questions tackled by the Hayabusa 2 missions, but the one that we were very interested in was to understand and quantify the redox state of the materials brought back by the mission. The point is, if you look at the different planetary or rocky objects in the solar system, there is a huge range of redox states. The way we plot this in geochemistry is relative to the iron Woostide buffer, named the delta IW. So when you're close to zero, that means that you are close to the equilibrium between pure iron and pure Woostide. So as you can see, there are some materials like Mars that is around -2 and +2 relative to the IW buffer. The Earth is more oxidized, particularly at the surface, because there's a lot of oxygen released this time. And here you have the different kind of materials and small bodies, including the moon and the different clans of meteorites. And this is very important for us to know where we start, or from what we start to build planets, because as a function of the materials you accrete from the planet, you will produce different kind of gases. This is the meaning of this plot, of this figure on the left side. If you start with some material that is very reduced, like the ansatite chondrite, you will mainly end with H2, CH4 gases, and no water and no CO2, and you will not build a habitable planet. So if you want to build something that is able to host life, then you have to control or to accrete something that is not too reducing. And so this is the big question. The redox state of the building blocks has a pivotal role on the setting up the habitability of the body that you are making. And the nature of accreting materials on Earth is widely discussed these days. And the question, and another question also, is the fact that when you look at the microstructure of chondritic materials, like the Semarcona chondrite you have on the left side, you see that you have many different kind of materials, ranging from metal to sulfides, silicates, phyllosilicates, so silicates containing water, and you have also organic matter. So a lot of different stuff that are not in thermodynamic equilibrium most of the time. And so it's difficult to have an idea of the bulk redox state of these materials if you do not have access to a specially resolved Mossbauer, or of course you can do that by Xanes also. And so this is pretty much the question that we were interested in, and the reason why our group has been selected by the JAXA. Was it possible to bring the samples from Ryugu directly to Sector 3 and measure the redox state of the different components of this material before any exposure to air? Of course, so these are some details of the mission. So it has been launched in 2014. In 2018, we had the first pictures of the asteroid. So you see the asteroid Ryugu. It's something that has been built by accreting materials from different sources. The size, the diameter of this asteroid is about 1 kilometer. And as you can see, there's a lot of boulders on the surface, so it was quite difficult for the spacecraft to land. You have one picture of the landing. There was actually 2 landings. The first one was designed to collect surface material. Then the spacecraft took some altitude. There was a blow-up happening then in order to create a small artificial crater. And then the spacecraft came a second time and collected some samples from deeper, say about 1 meter depth in the asteroid. in December 2020, so 6 years after the launch, the samples were brought back to Earth and landed somewhere in Australia. So this is the summary. It was a clear success. The samples were collected and secured in some stainless steel containers, never exposed to air before analysis. So this is the curation facility in JAXA. Again, the samples were not exposed to air. They were open in vacuum so that people could analyze the noble gases and the gas that got released during the travel from Ryugu to the Earth. And all the samples are currently stored under ultra-pure nitrogen. These samples have been curated, and the first information that was collected at this time, before the samples were sent to collaborators worldwide, were infrared spectroscopy collected by Micromega. So each single grain has some kind of identity card with an infrared spectrum. So this is how we studied the samples. So this one was studied for Hendrix, as you can see, and it was exposed to air. But most of the samples that I will show in a couple of minutes were analyzed without any exposure to air. It was directly, so the grains were sealed under nitrogen. It was sealed, they were sealed in a plastic bag and shipped to APS and analyzed directly in the plastic bags. We checked for the étanchéité, so it was airtight the whole time, and we checked this with some colleagues at IPGP in Paris working on noble gases, and so we were able to open the bags at the end of the experiment so that we were able to measure the noble gases trapped in the bag, making sure that it was completely free of terrestrial contamination. But before that, we had to calibrate and to get used to the beamline. And something that was critical for us was also to have a database for the most likely minerals in order to be able to fit the data. As you can see later, the samples are polymineralic, they are textured, and there's a lot of lines. So if you have no idea of the parameters and how to deal with separate minerals, it was pretty hard to get something that looks like a robust fit to the data. So we spent quite a long time to collect gem quality minerals likely to be present in the Ryugu samples. So this is a few examples of what we've done. We collected on natural samples with natural 57 ion abundances, the NFS and the conventional Mossbauer spectrum for each minerals, going from olivines with different amount of iron, pyroxenes, but also the clay minerals, because we knew from 1918 that Ryugu contained a lot of hydrous minerals. So we were able to analyze serpentine, smectite, and clinochrysotile with different amount of iron. And then we spent quite a lot of time playing with conus to be able to fit the conventional Mossbauer and the NFS spectra with parameters that were close enough so that we could be pretty sure about the robustness of the parameters derived by these two techniques. We also played a little bit with natural meteorites, and you have examples here of big samples where we were able to map the mineralogy of the iron mineralogy at the scale of a few tenths of microns on billets. And so you can see easily the different kind of spectra. Some of them are dominated by magnetite, some of them are are dominated by anhydrous silicates such as olivine. And there are also a series of different meteorites, because at this time we had no idea exactly what was Ryugu made of. So we collected typical spectra for a lot of different chondrites. And that was also very interesting to see that each clan of chondrites had typical SMS or NFS spectra, which means that NFS could actually be used to classify chondrites very easily, because you don't really need to fit the data. You just need to look at the main phases and where the bits are seen to be pretty sure of the kind of meteorite that you are looking at. So that was an interesting side project also. Because the samples, the results were quite complicated, and this was partly due to the fact, as you will see soon, that there is a lot of magnetite and pyrrhotite in these Ryugu samples. We also use for the first time, I think, the polarization simplification on natural samples. The idea is to use an external field of 0.7 Tesla in order to quench some of the lines that you find in magnetic materials, especially on this figure for magnetite, the lines associated with the delta N equal plus or minus 1. Because this produces spectra that are more simple to fit. It's we use this to determine the redox states of the grain, because it makes magnetite less intense, or the signal, well, it was more easy to deconvolve the contribution of magnetite and of clay minerals containing iron with different oxidation states. So now, focusing on the samples, this is how the Ryugu grains look like. So it's black. Looks like coal, basically. This was expected because we had spectra at this time, at the time of the recovery of the grains, indicating that the samples were probably close to the carbonaceous chondrites, like Orgueil or Allais or maybe Murchison. So it's black. It's there's no big crystals that you can see with naked eye. And then if you look at the mineralogy with the SEM, TEM, and tomography, this is more or less what has been reported in the first papers published. So the grains are relatively small, few tens of microns. The mineralogy is dominated by magnetite with different shapes. So you have rhomboids like this, and you have platelets. Now we know that there is at least the two ages for the magnetite and two formation age for the magnetite. The two different textures correspond to two different environments or two different history of the asteroid. We have also a lot of pyrrotites, and in some of the pyrrotites, I think it's Mike Zolansky from NASA was able to find inclusions, and analyzing the inclusion, he was able to show that there was CO2 and H2O trapped in this pyrrhotite, which give us an idea of the temperature where, on the place in the solar system where these materials got formed. It was pretty cold because it had to be beyond the CO2 ice line. So it was pretty much more or less where Neptune is now, so pretty far from the sun. And the last important class of minerals is clay minerals. So there's a lot of serpentine, as you can see here, and there's also smectite. So this is the mineralogy, and we knew that pretty much at the same time as when we collected data for the redox state of the grains. We also collected X-ray diffraction patterns on the beamline thanks to the setup installed on sector 3. And this is a typical spectrum for grain C61. And as you can see, there is a clear signal of smectite, serpentine, but also magnetite, pyrrhotite, pentlandite, and a little bit of dolomite. But we not pay much attention to this dolomite for the NFS. The first thing that we did, because we were lucky to have one large grain, about 400 microns in diameter, was to collect a conventional Mossbauer spectrum. This is the C0061 spectrum at the bottom. And after a couple of weeks, we were able to have a pretty good MS spectrum. And we played a lot to derive a mineralogical model for the iron mineralogy that could account for this spectrum. The reason why we paid quite some time playing with this spectrum is because it's easy to fit the data with conventional Mossbauer because it's an addition of different minerals, and you can see more easily what's missing in your fit. So we were able to fit the spectrum with 7 lines. 5 of them are sextets corresponding to magnetite and pyrrhotite, and 2 of them are more typical of iron 2+ and iron 3+ in silicates, let's say, or oxides. With this model, and so you can see the parameters in the table, with this model in hands, we fit the other spectrum that are not as good. So clearly we cannot say, we cannot derive very robust and univocal fit to the data for A26 and A117. But what was reassuring was the fact that taking just the model developed for grain 61, we were able to fit the data pretty well, just playing with the abundances of the different minerals. The first result that we were able to derive was that the magnetite at first order is stoichiometric, and the fact that iron in clay minerals contain both Fe2+ and Fe3+, which was already a very important result for us. Then we collected NFS spectrum, a lot of them. So you have a few of them that are shown here with different grains. Samples were collected in focused and unfocused beam with polarized and unpolarized configuration. And we fit the data. What was interesting was to show once again that we used all the parameters used to fit the data are very, very close to the ones derived by conventional Mossbauer. So all the data that I'm showing to you are self-consistent in terms of parameters. And you can see that there is some variability from one grain to the other, especially in terms of abundance of magnetite. The pyrrhotite is pretty much constant. It's about 20% of the total amount of iron. But the clay minerals and the magnetites are more variable. These are the parameters derived. As you can see, all the data can be fit with a bunch of parameters that are pretty much the same and pretty consistent with what was derived for the grain 61 in conventional Mossbauer plot. The plot in the orange diamonds all around. The only variability is for the isomer shift of this line that correspond to iron 3+. And so we'll discuss this a little bit later. Some of them are probably related to a poor quality of the fit, but some of them may suggest that we have 2 sites actually for iron 3+, one in serpentine and one in smectite, and they are not exactly the same coordination. We were able to look at the variability of the mineralogy at the local scale. So these are a series of samples of NFS spectra collected on 2 large grains. And you can see that the mineralogy is pretty robust. You have some changes in terms of intensity, but all these spectra can be fitted, just varying the amount of magnetite and clay minerals. So this is the same picture, the same spectra as shown previously. These are the polarized spectra, but as you can see, we were very lucky on A117b, because as you can see, this one is pretty different from the others. Looking at the X-ray diffraction collected on site, you can see also one large difference. The big difference with 117 as compared to the other ones is the lack of the 001 reflection of smectites that you find in at low angle. And so we were very happy to see that this grain was, or this position on this grain was probably documenting clay minerals with a large amount of serpentine and a very low amount of smectites, which allow us to look at the redox state of serpentine as compared to smectites, which was a major issue that was hardly tackled by even STIXM so far. If you look at the bulk redox ratio, this is the result we have in blue, and the spectrum that I just introduced, the A0117, has a very, very low redox state as compared to the other grains. This is very interesting because this tells you that serpentine is much more reduced than smectite. Most of the iron 3+ that we measured in clay minerals is accommodated in the smectite. And the other interesting result is that if you look at the isomer shift and the quadruple splitting of this fit, you end up with the conclusion that iron 2+ is in 6-fold coordination, but iron 4+ in this serpentine is probably in 4-fold coordination, which is pretty unusual for clay minerals. If we look at samples like C61, that is very rich in smectite, the QS and IS are a bit different, and we end up with 6-fold coordination for both iron 3+ and 2+, which is typical of smectite, and which also suggests that maybe the iron 3+ is formed by oxidation of the iron 2+ during metasomatism or fluid percolation on the Ryugu asteroid. Once again, all this data were collected without any exposure to air. Now, of course, what you want to do when you get this kind of samples straight from space is to compare to the materials that we have on Earth in our meteorites collections, and that look like, or look very much, that are very close to these materials. And so it was found that geochemically speaking, Ryugu is very close to the meteorite of Orgueil and Halley, so it's a CI chondrite. But if you look at the Mossbauer spectrum, and here I just compare the conventional Mossbauer spectra because it's we are all more used to this kind of spectra, you can see that there is a huge difference. If we look at Orgueil and Halley, there is something like 90% of the iron present in clays that is oxidized. Actually, it is known that it's not really clay, it's ferrihydrite. So, but most of the iron present that is not in magnetite is present as 3+. So this is the proof, and this was one major point of the science paper. This is the proof that actually probably the CI material that we have on Earth has been badly oxidized during the century, the last century, and that the pristine material for CI chondrite and CI asteroids is much more reduced. It's about 50-50 iron 2+ and iron 3+. So I'm going to stop here because I'm pretty long. I'm sorry about that. And if you have some question, I can answer, of course. These are the last slide.
Yeah. All right. Thanks, Matthew. Any, just maybe one quick question? If not, Let's move on to our next speaker. Next, we have Professor Volker Schönemann from University of Kaiserslautern, Landau, in Department of Physics. So he's going to talk about molecules. Right, Volker.
Yeah, thank you. Can you hear me?
Yes, yes, very well.
Great. So
we see.
You should see my screen, I guess.
Yes.
Good. I'm going to start.
Okay, good.
And thank you for having me to tell about our results, which we obtained at Argonne about dysprosium techniques on single molecule magnets. So what are single molecule magnets? They are two-level systems. Basically, you can store information into one molecule. That's the major goal of the development, the chemical developments. And the record high single molecule magnet, say 2 years ago, was a dysprosium compound with one dysprosium here in the middle and the ligand system around. It has a magnetization, a total J of 15.5. And that motivated us to start dysprosium 161 NFS and also NES. The requirements for single molecule magnets is a high spin ground state and an easy axis of magnetization along a set. So it should have a uniaxial magnetic anisotropy, but it can have thermal relaxation, so the magnetic moment can relax in that way. But it can also be thermally assisted quantum tunneling over the barrier, through the quantum barrier. And it can also have ground state quantum tunneling. That's the reason that these systems don't exist with hysteresis at room temperature yet. However, I should mention there is a science paper from 22 from the Berkeley group, Jeff Long. They prepared a dinuclear dysprosium complex, which has hysteresis even at 77K. So 161 dysprosium mass spectroscopy, a complicated hyperfine pattern here. If you do conventional techniques, but we decided together with Lena, my PhD, by that time, she's now in industry, to apply the synchrotron nuclear forward scattering techniques. However, due to the resolution of the detector, we only see transitions between these these lines here, or these levels, and that is basically shown here, where we have a typical beat period, which is reciprocal to the hyperfine field. So the beating is now a function of the magnetic hyperfine field of the dysprosium. That was successful. This is the complex here, which was prepared by our collaborators in Karlsruhe, the Andy Powell group. And we were very happy that we could get a very nice pattern here and deduce the hyperfine field of 582 Tesla, which is much larger than the expected hyperfine field of a free dysprosium ion. So the reason seems to be, or is definitely, a molecular one. So actually, one thought about 4F magnetism as a very localized magnetism. But in this complex, there is spin density also, not only on the dysprosium, but also on the ligands in axial direction. And this influence of the coordinating ligands on the Fermi contact interaction between the S and the 4F electrons, that causes this relatively high hyperfine field. And we were interested whether we could apply that as a microprobe for or nuclear probe for magnetization. So these here are measurements of the same complex in field at 4.2 K, and the hyperfine field could be deduced with CONUS positive, and the texture coefficient here is roughly following the magnetization of the sample. So we have basically actually the situation where we can use the dysprosium nucleus as a local probe for the electronic dysprosium magnetization. And here's another complex made by the power group. It has 2 dysprosium ions and 2 iron ions. So the iron ions are basically spectator ions for the dysprosium. And what they do? So in these molecules, they could replace the iron in the middle here by a diamagnetic aluminum. And when you look at the hyperfine field, that's 556 Tesla. But if you put the iron in and the structure is the same, the hyperfine field really increases by roughly 7 Tesla. So that's a molecular effect. And you have a polarization of the dysprosium core F electrons by D electrons of the iron 3. Of course, when you heat the sample, you turn on relaxation, and this measurements can also be used to determine relaxation rate of the dysprosium, as shown here, ranging from 130 nanoseconds at 4.2 K, still here at 10 K static, but then highly dynamic. And if you are in that regime, you don't measure anything in forward direction, and the signal comes back when you have the limit of fast relaxation of the magnetization of the dysprosium magnetization. I should mention, this is a complicated molecule, but the chemists, they can even manipulate the positions far out of the metal centers here. So this one had at this para position a hydrogen, and they could manipulate this position here by, as I said, a hydrogen or a methyl or a cyano group. And they did that before we started our investigations. And these 3 molecules here, they have different messpar spectra at 4.2 K, namely a doublet here and a magnetic sextet, which is a function of the modification at the para position. And we were interested whether we could also see some impact in the dysprosium NFS. And in fact, we see quite a high impact, 43 Tesla for the methyl, and 5066 for the hydrogen, 58 for the cyano. It's not in line with the change in hyperfine field of the iron here, but still it's an influence. And if you take if you take these complexes, here we took the H-modified complex and measured that at 4.2 K in increasing field, that's conventional messpar spectroscopy, this magnetic split part, 50% of the messpar spectrum went away. And we were left over with a diamagnetic state here, which is 100% antiparallel coupled of the iron spins. And the dysprosium, on the other hand, these are data now measured at APS under exactly the same condition. There we could infer that the dysprosium just act as they were alone. They act as an isolated dysprosium ions. Now, the interpretation of this strange behavior of the messpar part is there is a very peculiar ground state of this molecule, which has an iron spin actually of 0, but 2 degenerated doublets here. And if you crank up the field, you make the state to the ground state where the diamagnetic iron is preferred. And in the other states here, although diamagnetic, you have the hyperfine field showing up in low fields. Now we were also, of course, hunting for vibrations, and that came some time later. With the same complex here, we could measure the NRVS or NES pattern, and this is data here obtained at roughly 20K, and we could simulate this data with a density functional theory approach so that we could assign almost every mode we could see. And I only show you two here. This one, the 112 reciprocal centimeter mode, is a typical molecular mode where the dysprosium, what we look at, moves out of the axial position. It's very prominent here. We think this is one of the modes which supports relaxation. So this mode is basically unwanted if you want to have high temperature hysteresis. Here's another mode at 190 reciprocal centimeters, where the iron moves into that direction here, basically wanted, if you want to say so. During then COVID came, and we measured. We couldn't measure, we couldn't come to Argonne, but luckily last September we could go there, and we brought a new cryostat which allowed to have measurements at down to 4.2K and adjusting the APD detector very close to the sample, actually at a position of 5 millimeters. So the sample was at 4.2K, 10K, like we wanted to have. Here's an example. That's a measurement done in September on another type of an SMM on a dysprosium-containing metallocrown. Structure is here with some coppers outside here. And the DFT simulation, which was done afterwards, fits very well to the spectrum here. And the advantage of this is we can do top loading. So actually in that system, you can also load very oxygen sensitive samples. And the dysprosium CP systems, which have records now, they are, as far as I know, quite oxygen sensitive. With that cryostat also, we can do in the same experiment at almost the same sample position in NFS spectrum. That has not been analyzed yet because my coworker Tim got hit by a car in January. So analysis is a little bit pending, but we are very optimistic. And fortunately, he will be out of hospital in a couple of weeks. We also could measure another system, very beautiful, an iron dysprosium wheel. So here you see the dysprosium ions, dysprosium 3 ions, and the iron around here. As basically, they follow the magnetization of the dysprosium. And the ground state of this dysprosium wheel is a diamagnetic, but a toroidal state. And these states are very interesting because you can switch the direction of the dysprosium magnetization by applying electrical fields. Therefore, toroidal systems are also quite interesting. And we wondered about not only about the hyperfine interactions, but also about the phonons. And here you see a measurement done really at 4.2K on the dysprosiums at APS. And beforehand, we could measure iron 57 nuclear inelastic scattering, NRVS, on the iron systems. And we are at DAISY, and we are right now in the process of evaluation of the data, doing the calculations that are going on. I also want to share with you some results from Hamburg, from Petra, where we were interested to look at iron 2 containing molecular switches, which switch spin state from S equals 0 to S equal 2. So they don't change their magnets, but they change the spin states as a whole. You see here, nice color change. These systems also have a hysteresis. There was recently, some years ago, a paper which suggested that after light excitations of these S equal 2 states, you have amplifications of the high spin state in these systems driven by phonons in the nanosecond range. And that motivated us to perform a high repetition optical pump, iron 57 NRVS probe experiments with the laser, short delay time before the synchrotron pulse. By that time, we had a time resolution of 1 nanoseconds, which I show you. Now we can have time resolution even at 150 picoseconds. And when the next synchrotron bunch came, we didn't apply the laser flash, so that was the reference then. And then the next came and we measured that also. And here you see the two traces with laser on, which means probing here, and laser off, which means probing here, the ground state. And this is the difference here, experimental difference. This is a simulation based by a model, which I show you in a second. I should mention that was done with picosecond laser, and we can also do that now with a femtosecond lasers. Sample was cooled with the cryostream, which you normally use in crystallography beamlines. Here's the analysis. We see definitely changes which are small, 8%. Excitation, but that's also usually the case in pump probe experiments, people told me. And we could actually measure or determine these bands here where the high spin is excited, or the iron is excited to the high spin state, moving. Here the other band at 290 reciprocal wave number, another molecular mode occurs. And this mode is most interesting because here a low spin iron is moving. The high spin actually, which has been excited, is not moving. And we think this has a functional role in the self-amplification process. So I've been told I have 25 minutes, so I would like to come to the summary. And I must say dysprosium and iron are very nice local probes for both magnetic and vibrational properties for SMMs. You can do chemical spectroscopy actually with dysprosium by analyzing the hyperfine field, which can be influenced by coordinating ligands. One can observe magnetic relaxation phenomena on the nanosecond time scale, and by the same time measuring the dynamics, the vibrations. And also I gave you, perhaps interesting for future applications also at APS, a clue what we did with the transient NRVS experiments. Of course, I want to thank all the collaborators, especially the Argonne group. These were very hard experiments. I still remember the very first time, and also the last time where the cryostat just came at the very last minute, but it came out of the customs, and I was, of course, here are all people involved, and of course, very, very great acknowledgements to the chemist, and of course to my group, to Lena, who is now with BASF, and also of course to the DAISY people. And I thank you for your attention and these agencies for funding. Thank you very much.
Right. Yeah. Thanks, Volker. It's very interesting. Any questions, comments? Actually, yeah. Thanks for bringing up the optical pump roll experiment. It's very interesting from many perspectives. So actually, we have started we tried that also last year at the tin resonance. So,
Yeah.
but it was still under the data is under evaluation. There, we didn't do inelastic. We only did the forward scattering. So.
Yeah, I think one can do nice things.
Yeah, together with Dugan Hayes from University of Rhode Island. I think he's in the audience as well. Anyway, any questions, comments for Volker? Okay, then. Thanks again. So
thank you very much.
Yeah. So next, I'm going to hear from Professor Nikolai Lennart from the University of Michigan, Department of Chemistry. I think he's going to talk about enzymes, proteins. All right, Nikolai, please.
Thank you, Michael. Let me see if I can get this started. Right, can you see my screen?
Yes, no, it's good. It's in the, yeah.
Okay, laser pointer on. Yeah, so thank you for the introduction and of course also for inviting me for the workshop. It's a real pleasure to be here, really interesting program. And yeah, I'll tell you about, applications of nuclear resonance vibrational spectroscopy to elucidate the electronic structures of iron and O complexes. We've also worked on other systems. You can see on the bottom, we did some nerves measurements on cytochrome C, but I'm not going to have time to talk about that today, but there were also some interesting results that we got from this. So before we start with the science, I just wanted to talk a little bit about nuclear resonance vibrational spectroscopy, right, which is synchrotron-based technique, of course, which was first reported in the 1970s, but then really developed in the 1990s, and late 1990s became available, for example, at the APS now for the broad scientific community to use that technique. And it is a combination of nuclear excitation and molecular vibrations. So we use the Mössbauer effect to excite the nucleus and then measure inelastic scattering in resonance with this nuclear transition. And what's really interesting, of course, is that we can get a complete set of vibrations that now involve the motion of the nucleus we're trying to probe. So in a way, then, you can look at this in analogy to resonance Raman. In resonance Raman, we measure inelastic scattering in resonance with an electronic transition, and in nerves, we measure inelastic scattering in resonance with a nuclear transition. Another great thing about this technique is that there are no optical selection rules. As I mentioned, we can measure all the vibrations that involve motions of the probe nucleus. Another way to look at this is as quantized recoil, right? So when the probe nucleus absorbs your gamma photon, the recoil energy is now distributed over different vibrational modes, and that causes the ultimately inelastic scattering that allows us to detect these vibrations. But just like in Raman spectroscopy, inelastic scattering is a very inefficient process, and so you need a pretty big light source in order to do that, which of course is here the APS, where I've been going now for like 15 years or something like this. My group has been going to the APS to conduct these kinds of measurements. I think this is actually now outdated. I think there are now 5 synchrotrons where you can do nerves measurements. I think there's one in China now and another one in Europe. But still, it is an elusive technique from that point of view, that there are only very few locations where you can actually conduct these kinds of measurements. And of course, I'm also excited about the upgrade in terms of getting a higher flux and being able then to measure samples at lower concentrations, which will be very exciting going forward. Proteins cannot always be concentrated up to high enough concentrations, right, to millimolar range of concentration. So being able to go lower would really open up the door to do a lot more measurements. In any case, so I don't want to dwell on this too much, but I just want to highlight is the effort here. using, now, if we do this with iron 57, which is what my presentation is about, we need 14.4 kilo electron volt radiation to excite the nuclear transition. But at the same time, we want to look at vibrations, right? So the excitation profile of the beam has to be very, very narrow. The bandwidth below a milli electron volt, right? 1 electron volt is 8,000 wave numbers. So we're not going to resolve any vibrations on this stage. We need to get below milli electron volt in order to actually be able to see, you know, the vibrational sidebands, the inelastic scattering, and resolve them. And I think with the current setup at the APS, the resolution that we can get is about 7 to 8 wave numbers. So here's a data set. This was published back in the day by Bob Scheid and Tim Sage. It shows data for this iron porphyrin complex, this 5-coordinate NO complex. So at, you know, a frequency of 0 here, we have the elastic scattering, the Mössbauer line essentially, and then relative to this here, we have the vibrational sidebands, the inelastic scattering, our molecular vibrations. And as I said, the intensity here scales with the amount of iron motion in these vibrations, right? And so this is the stuff that we are interested in. Okay, so I'm going to tell you about some of the work that we've done applying now nerves to iron and O complexes. I have 3 different little stories I want to tell you about. The way we got really involved with this is looking at ferrocene nitroseals. So just taking a step back, nitric oxide is a very important signaling molecule in humans, right? It's involved in controlling the blood pressure. It's involved in nerve signal transduction in the brain and also immune defense. In our bodies, nitric oxide is made by the oxidation of the amino acid L-arginine by nitric oxide synthase, and then nitric oxide is detected by our universal NO sensor protein called soluble guanide cyclase. And in soluble guanide cyclase, you have a ferrous heme that is 5 coordinates, so it has axial histidine ligation. So it's kind of what's shown here. Oops, my cursor is jumping for some reason. So here is our axial histidine that is bound, and then you know, this is now the sensor unit. So then NO comes in and binds to the heme, and when NO binds here in the distal side, it induces a breaking of the bond between the iron and the histidine. And when that histidine here comes off, this helix here, it's connected to kind of swings out, and that causes a big conformational change that then activates the cyclase domain of this enzyme, and then the signal is you know, cascading from there, right? So we're really interested in looking at the electronic effect and how NO binding would activate here the sensor and how that induces breaking of that iron imidazole bond. Now, soluble guanide cyclase is very difficult to work with. And so what people have done in the field is usually looking either at simpler heme proteins that are easier to study, and myoglobin is an example for that. That has been studied quite a bit in the literature, so NO binding to myoglobin. And one interesting side effect here is that we can also study then hydrogen bonding from the distal histidine and see how that affects the properties of the iron NO unit. And what we've done in my group is looking at model complexes, and in particular here using this tetraphenylporphyrin, synthetic porphyrin ligand, and then we can make a 5-coordinate complex of NO or a 6-coordinate one where we have this 1-methylimidazole bound here in the axial position, which models a histidine, you know, in the proteins. And then, of course, we want now to collect the vibrational information, right? Because we want to learn about the trans effect. So we want to compare the electronic structures of 5- and 6-coordinate complexes, and we want to see how the bonding changes, right? And one good way to look at this is by measuring the NO stretching frequency, the iron end stretching frequency, analyzing this, calculating force constants, and then by looking at the force constants, we can see, you know, how the bonding changes between like the 5- and 6-coordinate complexes and what the electronic effect is that weakens this iron histidine bond. Since the iron NO unit is bent, we also have to look at the bending mode, because the bending mode could mix with the stretching mode in this bend conformation of the iron NO unit in these types of complexes. So here is probably the first data set that we ever measured at the APS, right? This is data on this model complex here. This is just on powder. The spectrum in black with natural abundance isotopes NO, and then the spectrum in red with 15N18O labeled NO. And you can see there are 2 modes that are isotope sensitive that show shifts when you label the NO. Right? And again, this is the data here in raw intensity or in counts on the detector. So of course, what's more practical is to actually look at the data, transform it into the vibrational density of states, because in the vibrational density of states, you have this very simple relationship, right, where the intensity now of the signal in the vibrational density of states just depends on this E² factor here multiplied with some kind of band shape function. You can also look at the directionality now, of the motion, so the direction in which ion is moving, and then this E² factor here, this intensity factor, can be directly related to the atomic displacement vector from normal coordinate analysis. And I'll come back to that in a little bit, but there's this very simple relationship which allows us to calculate the spectral intensities. And so here is now the same data set transformed into the vibrational density of states. We can now integrate these signals, right? We can calculate the E² factors in this simple way, and we can also now establish that for these two isotope sensitive modes, the relation of the E² factor, so the intensity is essentially 0.5, and we can use this as a further constraint for data analysis. But in order to really nail the assignments here, just going past just doing a DFT calculation, there were two more things that we did, and the first one I think is still one of the coolest experiments we've done is actually doing single crystal nuclear resonance vibrational spectroscopy, which was really pioneered by Bob Scheid and Tim Sage. And here are the data then again for our target complex, right? Where in blue, we have the data now where we have a single crystal, so all molecules, right, have the same orientation. We orient the crystal in a way that now here is the beam with the linear polarization, and now we orient the heme in parallel to the directional polarization. And so now we only get scattering from vibrations where the ion moves in the plane of the heme. So we get in-plane intensity, which is that spectrum here shown in blue. And then rotating the crystal, we get the out-of-plane intensity. And so now we can get the spectrum here. The red intensity is ion moving out of the heme plane, right? And so we can actually now, based on these measurements, distinguish the direction in which ion is moving. And what you note, of course, is that this 437 wave number band is exclusively out-of-plane polarized. There's pretty much no blue intensity here, whereas that feature at 563 wave number shows this kind of mixed polarization with blue and red intensity as well. So this is really important information now that we can use for our analysis. And again, going back to this equation here, right, the E² factor can be calculated from normal coordinate analysis, so from simple force field calculations. And then, of course, as you also saw from Volker's presentation, you can use DFT and then calculate the E² factors. And then from that, you can calculate your vibrational density of states. And this is something that is also really remarkable, right? Because when you perform these kinds of, normal coordinate analysis, vibrational analysis, in the case of IR spectroscopy or resonance Raman spectroscopy, you cannot calculate vibrational, intensities. You can calculate energies and frequencies and shifts with isotope labeling, but you cannot calculate the intensities. But for nerves, you can, right? And so that provides a whole nother level, of scrutiny in order to refine your vibrational simulations of the data. And so that's another really big strength about nerves, allowing us to do a much more rigorous analysis of the data, right? So going back now to this porphyrin complex, we then did what we call the QCC-NCA method, where we calculate a force field for the molecule of interest using DFT, and then we refine that force field using normal coordinate analysis. So it's kind of a combination of the two. DFT is not perfect, but we can refine then the calculated force constants in order to, improve on that. So what you see here in black is the powder spectrum, and then in orange, that is the simulation of the spectrum that we were able to do. And we can also then compare in-plane and out-of-plane polarization in our simulation, which is shown here. And I don't want to dwell on this too much, but you can see that we're able to reproduce the fact that this 437 wave number feature is fully out-of-plane polarized, and then we're able to reproduce the mixed polarization of that mode at 563 wave numbers, right? And to make a long story short, we can then assign them. So the 437 mode is the ion NO stretching mode, and then the 563 is the dominant bending mode, but has some stretching character as well, which is the reason why we have the mixed polarizations. You can also look at this, with the nice animation pictures. So here is the stretching mode. Iron essentially moves straight out of the plane of the heme. And here is the bending mode where the iron kind of moves on this diagonal. It's a dominant bending mode, but it has some stretching character as well. And, being able to simulate the polarized intensities really allows us to end up with a simulation where we have high confidence that we really figured this out. So if we take all of this together, then we get to our table here, right? Where we can look now at the force constants of the NO bond and the iron M bond. And this is the 6-coordinate complex. And then you can see when the imidazole falls off and you go to the 5-coordinate complex, both the NO bond and the iron NO bond both become stronger at the same time, right? So we can also say there is a direct correlation of these bond strengths when we go to the 6 to the 5-coordinate complex. And what that immediately tells us is that this is an effect of the iron NO sigma bond. So going from 6 to 5 coordinate, the sigma bond becomes stronger, or going the other way around, it becomes weaker. So I guess I looked at it here the other way around, going 5 to 6 coordinate. So we can take that information now and then kind of construct a molecular orbital picture that tells us what the significant interaction here is. And to wrap this up, we can put together kind of a bonding scheme. So again, we have an iron 2 complex. The iron is low spin, so we have 6 d electrons of iron 2, and then we have our NO bound to that with 1 electron in the pi star orbitals. I also want to quickly introduce the Ennemark-Feldherr notation here. Nitric oxide is what we call, in inorganic chemistry, a non-innocent ligand, which means it's redox active. And if you bind a node to a transition metal complex, you don't always know what the electronic structure is. So the Ennemark-Feldherr notation is an electron counting system that we just count the number of valence electrons of the iron NO unit. So we have 6 d electrons of iron, 1 pi star electron of NO. So we call this an FeNO7. And then the iron is in the low spin state. So we call this a low spin FeNO7. So then, when we let these two fragments interact, we end up with this kind of a mode diagram. And the key orbital here is this interaction between the dz square orbital of iron and this pi star orbital here of NO. This is a very covalent interaction. In the 5-coordinate complex, this is essentially 50-50 mixed. And this is really how this trans effect is communicated, right? When NO binds, it binds to the dz square orbital and it pushes off the imidazole in order to strengthen this sigma bonding interaction. And that's what you can see in the vibrational data in the way that the force constants change. So using, nuclear resonance vibrational spectroscopy, analyzing vibrations, analyzing bond strengths really allowed us to get to the heart of this electronic effect, that activates soluble guanide cyclase upon NO binding to the heme center. Okay, so this is kind of how I started, diving into the world of nerves and using it for hemes. And then from there, the next thing that we did is really going on and looking at non-heme ion complexes. And one result I want to highlight here is this series of complexes that we were able to study. So starting in the center, this is also an FeNO7 complex, but now we have, instead of a heme, we have this so-called TMG3 ligand here. So it's a non-heme ion ligand, and it's a trigonal bipyramidal structure. And I want to talk a little bit about the electronic structure of this species first. These non-heme FeNO7 complexes are very well known in the literature. They have been studied for over 20 years now, and we understand their electronic structure really well. But what's really new in our study is that we were able now to prepare the analogous either 1 electron reduced, so FeNO8, or 1 electron oxidized FeNO6 species, right, with exactly analogous structures. And that was really unprecedented. Before we talk about those, I want to quickly talk about the electronic structure of these kinds of species. Yeah. So as I mentioned, these have been studied for a while, starting with this, very important paper by Ed Solomon's group from 1995, where they looked at this first using especially X-ray absorption spectroscopy and also vibrational spectroscopy and MCD. And what they found is that these complexes are actually best described as high-spin iron-free NO minus, where the NO minus is in the triplet state, as you can see indicated here in my little bonding diagram. So we have a high-spin iron-free, all spins parallel, and then here is our triplet NO minus. So it has a very different electronic structure than the heme system, although they're both FeNO7s. We're looking at the bonding now, right? What is, oh yeah, Advanced notation we already explained. What is the nature of this bond? This triplet NO- ligand is really mostly a strong pi donor ligand. And you can see this if you look at, for example, this DFT calculation here, you look at the pi star orbitals of the NO- ligand, you can see that they have about 35% iron character, right? So this is a very covalent, very strong interaction here at the center really of the bond. We can also see this in this vibrational correlation here that we established, where we look at the NO stretching frequency versus the ion NO stretching frequency for a whole number of these compounds. The last one that we added is this one here with this really low frequency range that was published just last year. And this correlation here directly reflects this bonding model, right? So if the triplet NO- ligand donates more electron density to the iron center, the iron NO bond becomes more covalent, it becomes stronger. But because the donation comes out of these pi star orbitals, as you donate more electron density, the NO bond becomes stronger at the same time. So this kind of bonding model is really nicely illustrated by this direct correlation here between the NO and ion NO stretching vibrations and correspondingly bond strengths. Anyway, so all I'm going to say is we understand the FeNO7 compounds. So this one in the middle we understand very well, but now the question is, what about these other ones, these exotic ones that we were able to prepare? And here's some NERSC data where we looked at how ion NO bonding changes. Here is the FeNO6, the FeNO7, and the FeNO8. And then the data here, the final line, these are the 15 and 18O labeled complexes. And then we did our analysis again, QCC NCA analysis. So here are the experimental data. In this case, now we did not attempt to fit the ion ligand vibration with the TMG trend ligand. And you can see there is some deviation here between experiment and the DFT result. But we did fit the force constant of the iron NO unit, and we did it for all three compounds. And then you can see between the 6 and the 7 and the 8, as you reduce the compound, the iron NO bond becomes weaker, and the NO bond becomes weaker at the same time based on the NO stretching frequency that we were able to measure by our spectroscopy. But the ion NO stretching frequency here were all determined by a detailed analysis of the NERSC data. And then with this, we can kind of puzzle this whole bonding picture together. So again, the FeNO7 complex being in the center, if we reduce this complex by 1 electron, it is actually the ion center that gets reduced. So it goes from iron 3 NO- to iron 2 NO-. Correspondingly, the ion NO bond becomes less covalent, and you can see this here in the coefficients from about 35% ionic mixture into the pi star orbitals, it drops to about 25%. Right? And on the other hand, if we oxidize, we go from iron 3 to iron 4 NO-, and now the iron NO bond becomes more covalent, and actually this complex is kind of at the point of maximum covalency according to the DFT calculations. And then that means in this case, we have the strongest iron NO bond and the strongest NO bond. So again, vibrational data here being key, allowing us to analyze the detailed electronic structure now of structures now of this series here of complexes. Okay, we're almost out of time. So I'm just going to go to my last example, which is the series of highly reduced iron NO 8, 9, and 10 species that were prepared by Jonas Peters and his group, and they were first published here in 2016. And then we analyzed them using nuclear resonance vibrational spectroscopy. And there were two interesting things that we found. The first one was just simply the question, what is the best electronic description, of these complexes? Are these closed shell? Are these open shell systems? And here are the experimental NERSC data for the FeNO8 compound. And this is the iron NO stretch at 610 wave numbers. And then if you perform DFT calculations on closed shell models, which would essentially correspond to something like an iron 0 NO+ type electronic structure, you can see that these calculations here can reproduce the experimental data very, very well. But if you go to open shell system, so something like iron 2 NO-, and you perform DFT calculations on this, you can see that especially the iron NO stretch is completely off, right? And so that was really remarkable, because if you look at the optimized, the geometric structures that you get from the DFT optimization, there was almost no difference between the closed shell and the open shell structure. But the vibrational profile is very characteristic, and we can assign the electronic structure, for the series as being best described with the closed shell model. So that gets the smiley. And yeah, then of course we have NURBS data for the whole series. And what you note here is, remarkably, as you go from 8 to 9 to 10, there is very little that happens with the iron anode stretching mode, which was really not what we expected, right? And so that means that the redox active orbital here does not really involve the iron anode bond, right? Because there is no large effect really on that. So there's got to be another orbital that serves as the acceptor here. We don't have a lot of time, so I want to just kind of cut to the chase here, right? So here is the 8 compound with the iron 0 NO plus type electronic structure, and the iron NO force constant is about 4.5 millijoule per angstrom. If you add an electron, you can see the bond becomes a little weaker, but that's mostly due to spin polarization effects, because in the 9, now you have 1 unpaired electron as an S=1/2 compound. If you add another electron now, you end up with the 10, and the 10, you can see that the iron NO bond kind of recovers almost the same force constant. And what happens here is that you can see the interaction with the iron and the boron really becomes stronger in this doubly reduced compound, and that buffers some of the extra electron density that is sitting on the iron, is actually in a way stored in this inverse state of a bond here. And so if we're looking now at a ligand field picture, then we can see what happens in these complexes, right? So the redox active orbital is in the trigonal plane of the free phosphines of the ligand. It does not directly involve the iron NO bond. We can add 1 or 2 electrons to this the x square minus y square orbital here. As we do that, the complex becomes more trigonal symmetric. So the splitting between the xy and the x square minus y square goes down. And then you can see in the highly reduced complex, we get a little bit of extra admixture here of the pi star orbital, into these orbitals here, kind of like a delta bond. It doesn't contribute much to bonding, but it shovels a little bit more electron density into the pi star orbitals of the NO ligand. But overall, the reduction here all happens in orbitals that sit in the xy plane and does not directly affect the iron NO bond. Okay. So I'm out of time. This is a longer presentation here. I'm going to skip over this. There's 2 other examples for NURBS, and it's going to go to my acknowledgement slide. And of course, I want to particularly thank Urson, Michael, and Jong, who really helped me and my students, running all our NURBS experiments at the APS and helped us to collect all this beautiful data. So thank you for all your help over the years. And I hope that we're able to continue our fruitful collaboration when the APS comes back up. And thank you all for your attention.
Right. Yeah. Thanks, Nikolai. Any quick questions, comments? We're exactly on time. So, all right. So I guess it's time for a break. And then thanks for the speakers so far. So you all show very interesting, fascinating results. Hopefully, when we're back in a year or so, maybe a year and a half, so that we're gonna do more and then hear more interesting stories. So, all right. So let's take a 5 minutes or 4 minutes break. Come back 10:30 and start the next session. All right. So I'm going to pause the recording now.
Okay. I think we should get started. We are right on time. Thank you all for being here. It's my pleasure to chair this session, this next session. Our first speaker is Mark Pavlik. He is a new doctor. He just recently graduated from NIU. We had the pleasure to have him at the Sector 3 for quite a few years, where he conducted a very interesting and interesting work developing a new technique along with Sector 3 people. Mark, please take it away.
How do I do the? So yeah, I've been with Argonne for the last I think 4.5 years working on this technique. So we developed a. Oh, it does not let me do that. Hold on. There we go. So I developed a new X-ray spectroscopy method that measures the nanosecond timescale dynamics of liquids and gases at the atomic and molecular length scales. My research, we basically increased the counting rates, which allowed us to measure momentum transfers that were not reasonable to measure in the past. So with this nuclear resonance time domain interferometry, we can measure the diffusional motion of the liquids and the gases at different temperatures, pressures, and compositions. What's unique about this technique is we filled this little void where we can make measurements from about 1 nanosecond to about 10 microseconds and a momentum transfer between 1 and 100 inverse nanometers. So the interferometer is set up using a magnetized alpha iron foil as a source arm and using a stainless steel analyzer foil. And then we create an annular slit that allows us to collect the entire diffraction ring. So there are 4 possible scattering probabilities or paths through the foils and the sample. The first path is just electron scattering from the prompt. The second path is a nuclear resonant scattering from the foil, followed by the quasi-elastic scattering from our sample. The third path is the scattering, quasi-elastic scattering from the sample and the nuclear resonant scattering from the stainless steel foil. And the fourth path is the nuclear resonance scattering from the iron foil, followed by the quasi-elastic scattering from the sample and nuclear resonance scattering from the stainless steel foil. Each path has its own probability. So the probability of path 1 is just the response function from the sample and the delta function from the prompt. The second path is a resonant response function from our foil, and it has, because it's magnetized, we have a 2 I'll try to beat spectrum here, each indicated by omega 1, omega 2, and the prompt scattering from, or the scattering response function from the sample. The third path is again the scattering from the sample and the resonant function from our stainless steel foil. And the fourth path is the scattering of the response functions from the foil, sample, and stainless steel. If we want to look at the total scattering probability, it's just the sum of all these individual probabilities. And if we look at the scattering equation, it's just the absolute value squared of the probabilities. What we can do is we can eliminate anything with the delta function, and then anything with an omega 4, because those are very, the radial coupling regime, and it's very small, so we can basically ignore it because we are more interested in the quantum beat regime. If we eliminate everything and kind of simplify our equations, we're left with the following intensity equations, where we can see we have our sample response functions and our foil response functions. This is just the interactions with just the iron foil. This is the interaction between the sample and the stainless steel, and this is the interaction between the sample, iron, and stainless steel foil. If we look at the response functions for just the iron foil, it's simply just a can be modeled as a delta function from the synchrotron pulse, where J1 is the special beats. I'm hoping you guys can see my mouse, but this is these big beats we see here. These are the Bessel beats that we get to see. And then where T is just our effective thickness, tau is the lifetime of the nuclear resonant excited state. And again, these two omega frequencies gives me this small beating that we see here between these. Similarly, we can do this thing with stainless steel. It's just a single decay function. But what's more interesting is we're looking at the response function from our sample, which we can use as this as a model. So this is saying that our sample has some initial position at time t. We are interested to see what happens as the sample moves to a new position at some later time. So we try to write this intermediate scattering function that tries to explain the correlation between the particles at different times as well as different spaces. So here's what I'm trying to say is the particle is located here. At some later time, it has moved. and we are interested in analyzing where they move to. And if we look at this closely enough, we see that we can just simply add up all these different time-dependent phase factors, and this allows us to analyze the motion of the sample itself, or the dynamics of the sample. The way we want to rewrite this portion of our intensity equation is the dynamics of the sample. This is where this term is coming from the previous slide, and this is the dynamics, the static dynamic of the sample. So when we write our intensity equation, this is what most people are interested in, because this is the emitter scattering function, and we use the Cole-Austen-Williams-Watts stress exponential function as a model to define what's happening to the relaxation time. It's a widely used equation for most disordered systems, and it does a decent job allowing us to measure those relaxation times. So the way we set this up is we have to set up a calibration foils. So we start up with the stainless steel, with the magnetized alpha iron foil that allows me to determine the fitting parameter for the effective thickness and what my beat frequency is. Next, we do in the forward direction, again, just the iron foil itself, which I can measure the effective thickness. If I add these two together, it creates my interferometer. It also allows me to figure out what the isomer shift is. But I have this reference beating spectrum here, and this is the equation we use to fit this beating pattern. So what happens when I put in the sample? Notice that now we add the kWw equation here into the sample. This is both at room temperature. This one has the more forward direction. This one, we choose the peak scattering intensity, which is 14 inverse nanometers. And you can see this high-low B pattern is washed away when the sample is in there. So what is happening is this third term, this cross term here, is being destroyed. And what can destroy that? It will be destroyed, as we get to see. So quick, how we set this up is our initial setup used a single detector which allows us, using this geometry, we position where X is from this by using what our peak scattering intensity is. So that's the 14 inverse nanometers. If we do using this, what's nice about this is we get a high Q resolution. And when I mean high Q resolution, it's actually a low value. It's if we're measuring 14 inverse nanometers, here we're measuring anywhere from 13.5 to 14.5. Unfortunately, the count rate's very low at this. I think we're getting half a hertz or 1 hertz when we were doing this. So we tried to come up with a different method. So we tried adding a annular slit. So using basically the same geometry before, except now we put this gold annular slit in front of our APD detector, which allows us to collect the entire diffraction ring instead of just a small portion of it. We made three different slits. Using the 1 millimeter annular slit, we increased the counting rate by 2 orders of magnitude, which allowed us to do a full range of temperature measurements in a short amount of time. Unfortunately, when we use these annular slits, because of the way the geometry is set up, that spread in momentum, or the delta Q resolution, or the Q resolution, is increased. And there has mainly 3 factors that are affecting the resolution. It's the thickness of the sample, the distance between our sample and our annular slit, and the annular slit width itself. So the Q resolution is based on these angles. So if this is my sample, this is my slit width, this is the distance or the radius to the center of my slit, and then the distance between the center of the sample to its slit width itself. So L is kind of what we use to determine the momentum transfer, the Q value, and then the other values are relatively fixed as we do this. But this is the geometry that kind of determines what the delta Q resolution is. So for our 3 slits, if I plot the Q value versus delta Q, this dashed line is that 14 inverse nanometers. This is what that peak is for glycerol that we were using. you can see for the 1 milliliter slit that it has a plus or minus 2.7, which means instead of measuring 14, we're measuring closer to like 11 to 7. And the smaller slits, the resolution gets better, but with the smaller slits, the count rate definitely goes down. Going back to the previous few slides, we want to talk about the intermediate scattering function and what destroys that third term. So using the mode coupling theory, when that intermediate scattering function is approximately 0, we consider that sample in that liquid phase. Whereas as we start to cool the sample or go to the supercooled regime, that intermediate scattering function is no longer 0. And we can start measuring what the relaxation time is throughout this process. So here are 2 examples. So the red, the blue is actual data, the red is the fit, and the green is the simulation. Here we want to look at what happens when we have a small relaxation time, which indicates a fast relaxation rate. When I do that, you can see the high-low beat pattern is being washed away. So this is like that room temperature measurement that we saw in the beginning. What is happening is the intermediate scattering function, again, goes to approximately 0. So this term of the equation is being eliminated. When I do that, it can do that in 2 ways. If I'm using the KWW equation, I can either take this non-organicity term or this FQ factor and make it 0, or I can make the relaxation time 0. Either or eliminates that term. So I have to be careful when I get closer to the room temperature, because when my fitting models would try to blow up my relaxation time when this goes to 0. So I had to do some analysis that kind of helped me throughout the process of getting a better relaxation time. And then you can see the similar thing is when I go to a frozen sample or a very cold temperature, my relaxation time is extremely large, which means a slow relaxation rate. The green line again is the simulation saying that the relaxation time is at infinity. Again, there's a red curve hidden behind there that you want to see as well. Again, the blue is the data points. So in this case, this non-intermediate scattering function is adding a fractional portion of this, and is actually in giving us a fraction of this instead of eliminating it. And we can see again, this goes back to what we saw with just in the forward direction of just the foils, the high to low, high to low. We can measure the relaxation times by analyzing the depth of the troughs and peaks between these 2 graphs. So here are, for example, I'm using different momentum transfers. So I have 20 inverse nanometers, 14 inverse nanometers, 5 and 2. And what we're doing is we are kind of zooming in and out of our molecule here. So here at 20 inverse nanometers, I'm zooming more into more probably the individual molecule itself versus, so this is why I see this fast beating pattern. Whereas I start to zoom out, I'm looking more at a group of particles, and you can see that the relaxation rate is, my relaxation rate is decreasing as I move out. Again, we see this.
You have 1 minute to go.
Oh, sorry. I have the relaxation. This is just the different relaxation times for the Q values. We can do the same thing for the different temperatures. As we go from a warmer temperature to cool temperature, the molecules again start to bind them up. So this is just a plot of them at different temperatures. We can see we are reasonably well with other literature out there. And if we look at the mean relaxation time, we can start to look at the different alpha and beta processes of these 2. And finally, for glycerol, we were able to do a digits narrowing on that using the smaller annular slit. Again, it agrees reasonably well with other data out there. So what we are able to do is increase the counting rate by 2 orders of magnitude. We hopefully presented a clear model to represent time domain or nuclear resonance time domain interferometry using resonant foils and non-resonant samples. We were able to do some digits narrowing, and for glycerol, we found that the glass transition to be about 185 Kelvin, which is within the literature that we found out there. With that, I will take any questions.
Actually, we are a little bit tight in time, but we have sometimes at the end for discussion. So I would like everyone to hold on their questions to the end of the session. And please stay, Mark, and everyone else, if you can, please stay in the meeting. It's my pleasure to introduce the next speaker, which is Brent Foltz from California Institute of Technology, and he had made beautiful NRICS and NFS studies at our beamlines and other beamlines as well. Please, Brent.
Well, thank you, Barbara. Let me make sure things work here technically. Does this look like the right mode?
Looks good.
Okay, great. So I'm going to talk about phonon and spin thermodynamics, which uses NRICS and nuclear forward scattering. But the basic concept was really set up around the idea of doing thermodynamics. So I'll have to talk to you a little bit about entropy and free energy and how that relates to thermal expansion. This is in particular, this work by Stefan Lohaus, who's just finished his PhD draft as of yesterday. And he has got a study on iron 65, nickel 35 INVAR, which, as you know, has zero or near zero thermal expansion around room temperature. He did experiments as a function of pressure around room temperature, and we can explain the INVAR effect thermodynamically now. The new piece of it is not the magnetism, but it's the phonon part, which has been neglected up to date. So I'm going to start by talking about thermodynamics. And here's entropy, the classical entropy on the left and the statistical mechanics entropy on the right. Boltzmann, his expression is the one we've primarily been using. The omega is a number, a pure number, and it's a count of something. The physical entities that we count need to be thought through, and the way we count them needs to be thought through. For the classical thermal, all you need is the heat capacity. It turns out it also gives you a number of other relations that allow you to design things very nicely, to do stat-mech experiments, which is really what we're doing with the nuclear resonant scattering work. Okay, you all know about the configurational entropy, I think. Here's equiatomic red and blue alloy. We put a blue atom on the upper left here, and the next ones go down randomly with two possibilities, irrespective of what their neighbors are. So that's logarithm of 2. That's our W or our omega, and that's per atom. On the right, we could have a blue or red here, and the rest are all defined. Once we put down the blue, then we know its neighbors, and that is basically 2 per Avogadro's number, which is 0. So that's sort of the range of configurational entropy. Log 2 is 0.69, and 0.69 kb per atom to 0 is about what we can expect. That's a matter. That's how we arrange matter in space, basically locating the nuclei. And then the electrons move around, and there's no additional entropy with that, unless we count spins or mixed valence states. But for the metals we'll look at, the spins will be important, although not the mixed valence. The energy is the other place that we put the heat when we're heating up a sample and give a heat capacity. And most of it is vibrations of nuclei, the phonons. We can also have spin excitations and excitations of electrons above the Fermi level of a metal, for example. This is all textbook stuff, but the thing that's tricky is that these excitations interact with each other, and the energy cost to put in another phonon when a lot of other are present and the atoms are displaced, that varies with temperature, for example. And likewise, the energy to put in a spin excitation varies with how many phonons are present too. So we have these other interactions we have to take into account. Here's the big scale. The combinations of atoms on a lattice are up here in the left at this 0.69 kb per atom. There are people now doing high entropy alloys where they can double or maybe almost triple this. but is still less than 1 kV per atom most of the time. At 1000 Kelvin, there's a large amount of entropy that you can associate just with harmonic oscillators using the ground state density of states, if you like. But as the crystals expand, their frequencies change. We call this a quasi-harmonic correction. Here's the excitations of electrons. We'll worry about phonon-phonon interactions and spin-phonon interactions too. So these are all the pieces of entropy that need to be correct if you're going to do thermodynamics and account for heat capacity. We spent a lot of time doing this basically, and we found that these two reconcile very well with each other. All right, so thermal expansion. Why does a material expand? Well, it expands with temperature because its free energy is lower at a larger volume at a higher temperature. So I do have to do some thermodynamics here, but it's not too painful. Here's the free energy, and we look at how it depends on volume because we're looking at expansion. So that's the two terms that we get. And these are, by the way, equal to each other because this is the definition of pressure. How does the free energy change with volume? So if the pressure applied is 0, then these two terms have to be equal to each other. And this is a condition that we're going to be using to get the volume at a given temperature. Okay, so basically thermal expansion matches an elastic energy of stretching the lattice versus the improvement in entropy that you get by, say, lowering frequencies with the increased volume. So this is the big question now is why does the entropy at the stat mech level change with the volume? Well, the expression for a harmonic oscillator and its entropy and a distribution of them is here. We're in 3 dimensions times Boltzmann's constant. We need the phonon density of states, which is this G, it's normalized to 1. And this is the entropy effectively of mixing of bosons. There's a more familiar entropy of chemical mixing, but this is basically the boson equivalent for it, using the Planck distribution for the occupancy factor here instead of a concentration, let's say. And of course, our frequencies are the key thing. They set what the energies are. And the main thing we have to know is really what the frequencies are. And that's how do they change with temperature and volume. So there's 2 things we need to look at. One of them is how they change directly with volume. We call that quasi-harmonic behavior. Basically, we stretch the bonds. They usually get weaker. This is actually pretty easy to calculate these days just by expanding the lattice in a density functional theory calculation and recalculating what the forces are when you're displacing atoms, for example. This is called quasi-harmonic theory. There's a package PhonoPy that does this. It's widely used. You'll see it in a lot of literature that tries to explain thermal expansion this way. It's missing a big piece, and that's that when we go up in temperature, the frequencies change just because the atoms are being displaced. You already have phonons, you have displaced atoms. So the energy cost to add another one is changing. This effect can be as big or bigger than what's expected out of quasi-harmonic theory. So you really have to do both. How do the frequencies change in volume and temperature? So that's just a little background here. Now we have to get spin entropy, and that's part of our work here. This is a little bit beyond what's realistic with density functional theory, but our collaborators, computational physicists at Boston College and Weissman Institute now with Lily Hellman, had developed a scheme to try to put everything together on a lattice, the atom displacements, the chemical disorder, the spin magnitudes, localized as Heisenberg models, and their orientations, and take a whole set of snapshots basically and calculate the energies of all of these things. So unfortunately, there were too many degrees of freedom to really do this. So they call this measurement guided first principles calculations. And what they really get is a pressure as a function of volume and temperature. That's how the energy changes with volume. And then you have to weight that by the number of elements in the ensemble, which have this piece of I. That's the key thing. And they don't calculate really all of that. They get the magnetization as a function of temperature, and they throw away the elements in the ensemble that are too far away from the experimental magnetization. Otherwise, their computations are pretty impressive. These are plane wave pseudopotential codes with spin orbit coupling, chemical disorder, displacements that cause changes in the exchange interactions between spins, and the temperature and pressure induced vibrational and magnetic order. It's been very valuable for us working with them because we could sort out the spin phonon interactions with their work. Well, Guillaume in 1920 got the Nobel Prize, putting off Einstein for a whole year to 21 for services to the physical precision technique by his discovery of the properties of nickel steel. This is basically a discovery in metallurgy, which won the Nobel Prize in physics, a little unusual, but the thermal expansion coefficient is here, and the concentration of nickel and iron are along here. He wasn't aware that there's phase transitions between BCC iron and FCC nickel. He just did these compositions and nevertheless discovered the anomalous thermal expansion. Notice how delicate it is. You have to be almost spot on in the composition within 1% or so, not like other physical properties, the thermophysical properties like elastic constants, for example. Now, he knew there was something to do with magnetism here. And here's a plot of the length of the sample versus temperature. And the part up here at high temperatures is pretty normal, and that's what expansion was that he expected. At low temperature, the expansion gets smaller, but this flat part he knew was associated with a Curie transition and a magnetic transition. So this led to a large number, hundreds, maybe thousands of papers to relate the magnetic behavior, which has a high spin at low temperatures, and it loses its orientation with temperature, as magnetism does. But this also has a high volume. So this counteracts somehow a lattice behavior. And this was put together, especially in 1963 by Weiss, who published in the Proceedings of the Royal Society, London, I think, saying that there's a two-state model, high spin, high volume at low temperatures to low spin, low volume at higher temperatures. And this sounds so appealing that it's led to a lot of other computational work. And here's an example of one of the early electronic structure calculations in polarized states. You can see there's a high volume preference for, say, larger spin and lower spin, smaller volume down here, and a couple of minima in the potential surface. But this has been a quantitative failure. Look how big these changes are. These are a few percent in the lattice parameter, which is not the scale of things. And there's no role for phonons in this. And this is something we've been looking at for other reasons. And usually we explain the thermal expansion by looking at anharmonic theory along with quasi-harmonic for comparison, explain thermal expansion. This is really missing. It's surprising. So we made our own INVAR with iron 57. This is from sector 16 diffraction data. We looked at it under pressure. Now I'll explain why in a minute. But we were lucky that we have zero thermal expansion between room temperature and about 390 Kelvin for pressures of 3 gigapascals. We did not know this when we started, what we were going to get. It hadn't been measured, and it's lucky it was in this range. We can get a thermal expansion versus pressure out. That's the inset here. And it's not great data, but this is not really what we were aiming to do precisely. But generally, there's the INVAR effect goes up to about 3 gigapascals. Here's the Curie transition. I'll point that out later. And so it doesn't go all the way up to the Curie transition. Then it gets pretty normal beyond that in the thermal expansion. So why pressure? Well, let me go back to my second thermodynamic slide here. This is the free energy as a function of pressure and temperature. And we can take the derivative with respect to pressure or temperature and then take the other one. So doing it in the order of the temperature first, this gives you the entropy, because this is minus TS as a term contributing to the G. Then we take the next derivative with respect to how do the entropy change with pressure. Now we can reverse the order of these differentiations, take the derivative with respect to pressure first, and that gives you a volume because it's a PV term in the free energy. Then do the temperature derivative, and we get how does the volume depend on temperature? That is the thermal expansion. Okay, so this is the relationship that we need, a Maxwell relation between the entropy, its pressure dependence, and the thermal expansion. That's why we did those measurements versus pressure. For INVAR, we know the thermal expansion is 0. So that means that the total entropy with respect to pressure has got to be 0. And the question is, what are the terms that sum up to this? Can we get cancellation of magnetic entropy and photon entropy, for example? That was the experiment. Well, I'm not going to go too much on the details here of how we did these things. I think that you have seen samples in diamond anvil cells here. They're very small, and the structure of the up through the beamline is here for the nuclear resonant inelastic X-ray scattering. Also skip this because I think you all know the timing trick of how to separate the synchrotron flash and all the X-ray processes from the nuclear decays. This is something that is essential for these measurements, really, at least to date it has been. And you also know how the nuclear forward scattering works with the quantum beats. This is my attempt on the bottom to show how you would have a slightly different frequency decay photon coming out from a different nucleus with a little energy shift of epsilon and give you some beat patterns here. And of course, the iron is much more complicated than just 2. But here's what we got for INVAR. This is the pressure dependence of the nuclear forward scattering at 300 Kelvin. The fits using CONUS are these red lines here. And with your eye, you can see pretty well that it's magnetic down here, and up around 4 gigapascals, it goes non-magnetic, and we get a thickness beat here. But basically, you can see the range where we have the magnetic behavior below about 4 gigapascals, and then we can look at the magnetization, the hyperfine magnetic fields versus pressure here, and use that for our magnetization. So our theory colleagues did this as well, as I mentioned. They've looked at iron nickel in the spin-aligned ferromagnetic state, which is actually pretty much 0 Kelvin. Room temperature already has a fair amount of misalignment here in the spin orientations. The iron spins dominate. The nickel spins, these little blue ones here, are much smaller. And by the way, they tend to stay aligned a little bit better with temperature. So all the action is with the iron, which is great because we're doing iron 57 work. The paramagnetic state, as you expect, would be more random. And this is the pressure dependence of the magnetization. Our points are here, the black ones. There's been some X-ray magnetic, circular magnetic dichroism experiments. There's quite a number of measurements. The computational work is the red crosses here. This is when we gave them, it's kind of a closed loop though, because we kind of gave them magnetization information to try to figure this out. So it's not quite a fundamental principle, but it's interesting to look at this. As I said, it's not a 0 disorder at room temperature. And if we overlay it with the magnetization as a function of temperature, aligning it up at the Curie point, we get this. And here's our room temperature behavior, which is in both of the curves. And it might be that there's a little bit more of a curvature for the pressure dependence of the magnetization than there is in the temperature dependence, but I don't think very much. So we have to get the magnetic entropy, and we have some endpoints that we know. We know that there's no magnetization at the Curie transition, either in pressure or in temperature. We'll assume that the magnetizations are the same there. They're just short range order. Now, the short range order might vary a little bit between these two. We also know we have an endpoint at room temperature, which is in both sets of data. So we can get the entropy from a calculated curve below the Curie temperature, and we scale it by calorimetry. We have magnetic enthalpy from calorimetry, and fortunately, classical thermodynamics comes to the rescue here. So here's what we get. Here's how the magnetization, the change in magnetic entropy changes with pressure. The reference point is 0. It's not really 0. And up to the Curie transition, both the calorimetric entropy by temperature and the nuclear forward scattering by pressure are in pretty good agreement. Maybe there's a little more curvature for the nuclear forward scattering. I also won't go through how the monochrometers work for doing the nuclear resonant inelastic X-ray scattering. It's a marvelous thing to explain to a general audience, but I don't think we need it here. But I'll show some data. Here's the INVAR data for room temperature on the upper left with an elastic peak here. But you can see nicely the cutoff of the 1 phonon scattering, the 2 phonon parts, and so on. Now, as I said, we're only looking at the iron 57. So the question is for the nuclear scattering, what are the nickels doing in the vibrational density of states? We had actually done some inelastic neutron scattering on this, and that gave us this dotted red curve here. And the NRIX has got the black curve, similar resolutions actually, amazingly. But generally the weight is the same. There's no different weighting where the nickel atoms are contributing to a different part of the DOS. And this had been studied also with other iron nickel alloys by a former student, and it looks like the partial DOSes of the nickel and the iron are the same. That makes the entropy interpretation a lot easier. Now you look at it as a function of pressure. There's a number of things to see. Generally it stiffens, although below the 4 gigapascals, the longitudinal mode peak at around 33 MeV doesn't really change that much. It's mostly in the transverse modes. All right, here's the phonon entropy versus pressure. This is falling because we're getting stiffer phonons and the atoms don't move as much, so the entropy goes down. And our experimental points are these up to the Curie point, then it gets kind of flat above that. The theory group was able to turn on and off the spin-phonon interaction, and so they actually got a explanation for this curvature behavior here, claiming it's related to how the photon affected by the spin disorder in the system. But this is the essence of INVAR right here. Here's the phonon entropy. It's decreasing with pressure, and the magnetic entropy is increasing, and they cancel each other out really quite well. The electronic contributions, which were also from the theory, didn't change nearly so much with pressure. So this is the essence of INVAR. It's a very delicate balance between the phonon entropy and the magnetic entropy, their pressure dependencies specifically, and it's aided by the spin-phonon coupling. By the way, we can individually plot out what the thermal expansion coefficients are from the phonons and from the magnetism. And it turns out in the INVAR range below about 3 gigapascals, they don't stay constant. They're actually both increasing, which I thought was kind of unexpected. And there's some crazy behavior at the Curie transition, probably because our pressures aren't stable. Above it, we get to a normal thermal expansion. But here's the summary. So we're got a delicate balance where the total entropy is 0. Magnetic balances out the vibrational part of the entropy. And this is, I think, a very promising direction for future work. We can look at other anomalies in thermal expansion in magnetic materials, of course. The temperature dependence of the bulk modulus, and which is null in LNVAR. I think we got data on that look good. And we can look at spin phonon coupling here fundamentally, or maybe how we can enhance magnetocaloric effects by coupling into the phonon bath. After the upgrade, I think things look really good for the NRIX. nuclear forward scattering for magnetization will be okay, I think, in the 48 bunch mode. We're just looking at how it varies with temperature. And of course, we can access higher pressures if we need to. We do need to get precise control of temperature and pressure to do this type of work. And I think doing the phonon part and the magnetic part are interesting together and promising. And this is a good combination of both nuclear forward scattering and nuclear inelastic phonon scattering as well. I think the two of them are both essential.
Great. Thank you, Brent, for the wonderful presentation. I think we were just right on time. So if you all agree, we move on to the next presentation and we hold on questions on the last time slot of this session. And so let's move on with the next speaker, who's Barbara Raschbacher from UC Davis, and she's going to be talking about minerals being measured at sector 3, I believe. Please go ahead.
Hi, thank you, Barbara. Can you see my presenter mode screen?
Yes, it looks good.
Okay, perfect, great. Yeah, thank you so much for the invitation to talk here today. So I will present on characterizing natural amphibole grains through a combination of microanalytical techniques, which include single crystal synchrotron Mössbauer spectroscopy. And before I'm going to dive into the methods we used and present some of the results, I would like to start off with giving you a little bit of motivation why I in particular focus on amphibole grains. So I'm an igneous petrologist, and as such, I study magmatism, and in particular, my research focuses on subduction zone magmatism. So in subduction zone, as you can see here in a schematic cross-section, magmas are generated in the mantle above the subducting slab. They then can further ascend towards the overlying crust, where they can undergo chemical and physical differentiation processes. So these processes change the chemical composition of magmas and ultimately led to the formation of continental crust. So why are we interested in studying subduction zone magmatism? Well, there are several reasons, but I summarized here what I think are the three most important ones. So first, subduction zones are the site of major violent volcanic eruptions associated with a really wide range of hazards. So we would like to understand how volcanic plumping systems work in order to mitigate those hazards. And secondly, magmatic systems in subduction zones are associated with economically important ore deposits. And last, as I already mentioned, subduction zone settings are regarded as the major site of new continental crust formation. And continental crust constitutes the outermost shell of our planet, and it's compositionally very distinct from the interior, from the mantle. So we really want to understand how we form continental crust in subduction zone setting, because it's important for a really wide range of processes. For example, it's believed that the formation of continental crust was really, really important to allow for the evolution of life on continents. So you can see we need to understand the chemical and physical evolution of subduction zone magmas. But how do amphibole minerals fit into this? How do they relate to subduction zone magmas? Well, amphiboles are actually a very common mineral in subduction zone magmas. They crystallize from a wide range of compositions, and they are also stable or crystallized over a wide pressure and temperature range encountered in the crust. So this is illustrated here in a schematic phase diagram for subduction zone magmas, where you can see the amphibole stability field highlighted in green. So given those characteristics, amphibole is a really valuable tool to study subduction zone magmas. So amphibole mineral chemistry, in particular major element chemistry and also trace element chemistry, can be used to study crystallization condition of magma, such for example, magma temperatures, magma pressures, or also the composition. So that's why I focus on amphibole in subduction zones. But what are amphiboles? So for those who had never worked with those kind of minerals, amphiboles are silicate minerals with a rather complicated structure and chemical composition. As you can see here, amphiboles are made up of silica oxide tetrahedra, which are lined in double chains. And those layers of double chains are bound together by various octahedrally coordinated sites. And on those sites, we have a wide range of cations which can be incorporated and substitute with each other, which results in a wide compositional range within the amphibole group minerals. So among those cations are also ferric and ferrous iron, which is the focus of the study. So you have this wide range of compositions, but you also contain volatiles in amphiboles, such as water in the form of OH, and also halogens like fluorine and chlorine. And again, this compositional variability really highlights the usefulness of amphiboles in answering a lot of questions we have about subduction zone magmas, because they're capable of recording temperatures, pressures, and melt compositions, and even volatile contents. So if you now go look at natural amphiboles, so an amphibole, for example, you can find in an igneous rock, which erupted at a volcano, and you look at the sample in thin section under the microscope, you will see that a lot of amphiboles have inclusions of other mineral phases, such as, for example, iron titanium oxide. So you can see that here in the first picture. That's a microscope image of an igneous rock. But amphiboles can also have intragrain compositional heterogeneities. So this is mostly manifested in sonation patterns. So in the second picture here, you can see a backscatter electron image of an amphibole, where you clearly can discern a compositionally distinct core and a rim which grew around it. And then last, amphiboles also often show alteration textures. So in the last picture here, you can see those black rims around individual amphibole grains. And those are really textures which have been acquired after the crystallization from a magma, probably during ascent and eruption at the surface. And they are able to modify the primary magmatic composition of amphiboles. So if you deal with natural amphiboles, which have inclusions, compositional sonation, and alteration texture, that really highlights the necessity for the need of a high spatial resolution and a high precision technique, which are capable of avoiding analyzing iron-bearing inclusions in amphiboles or alteration textures, and which is able to discern different compositional areas within individual grains. So in the remainder of the talk, I will focus on two parts. So first, I will present to you a new workflow me and my collaborators developed, which aim at integrating different microanalytical techniques on the same area of individual amphibole grains. And in a second part, I will apply this workflow to volcanic amphiboles. And in particular, I will pose the questions whether ferric over tall iron ratios we can determine using single crystal synchrotron mass power spectroscopy correlate with ferric over tone ratios in the melt from which they crystallized, and what post-crystallization processes could potentially modify those ferric over tone ratios in amphiboles. Okay, so let's start with the first part. So we developed a new workflow consisting of 5 steps, combining different microanalytical techniques. And again, the goal here is really to be able to correlate different data sets from the same area on individual amphibole grains. So we start off with a detailed petrographic investigation of amphibole textures and reaction relationships in thin section under the microscope. And then we take the rock, crush it, and sample out individual amphibole grains. We mount them in epoxy and polish them for major element analysis using the electron microprobe. And we also determine the water content in amphiboles and the hydrogen isotope composition. And we do that by using secondary ion mass spectrometry. So in the next step, we then remove those amphibole grains from the epoxy mount and mount them on a micromesh for X-ray diffraction. And that's a really crucial step prior to taking the individual amphiboles for synchrotron mass power spectroscopy, because with XRD, we can determine the crystallographic orientation of each individual grain. And you will see in a moment why this is really important. But then the last and final step is to take the individual amphiboles, mount them on a plexiglass slide, and analyze them for their ferric over total iron content at beamline 3, the synchrotron mass power spectroscopy. Okay, so if you want to learn a little bit more about the methods, I refer you to a recently published paper in American Mineralogist. Okay, so a little bit about the setup. So we collected time and energy domain spectra at beamline 3 using 2 different setups. So those are illustrated here. The first one operated during 24 bunch mode filling pattern of the storage ring. And the second one operated during the hybrid mode filling pattern of the storage ring. So the second one is the new setup developed by Tom. and involves 2 high-speed shutters and also allows the insertion of a Mossbauer drive to collect not only in the time domain, but also in the energy domain. And by combining those 2 setups, we're able to collect time domain spectra with delay times between 20 and up to 450 nanoseconds for our samples. So we also collect spectra along different orientations. So you can see that here in the first panel. And the reason we do that is because of the linear polarized nature of the synchrotron radiation and the polarization dependency of the hyperfine interaction at the iron nucleus. So by doing that, we analyzed at least 2 orientations for each individual grain. We collected spectra on, and by doing that, that really helps us to disentangle and discern between the contributions of crystallographic distinct ferrous and ferricite in the amphibole structure. We then take the spectra and fit them both energy and time domain spectra with the Kono software, which is shown here. And we also collected data with a stainless steel reference flow to determine the isomer shift. So here's an example of some of the spectra we're able to collect using energy and time domain and the 24 bunch and the hybrid mode setup. So in panel A and B, you can see example of 24 bunch mode energy domain data collected again for an individual crystal along different crystallographic orientations. And then in panel C and D, you can see examples of a time domain spectra and an energy domain spectra collected during the hybrid mode setup in the same orientation. And then Konos is also capable of taking or calculate energy domain spectra, which you can see here in E, using the best fit values from the energy domain model we developed. Okay, let's move on to the second part of this talk. So now I will talk about an application of this new workflow to volcanic amphiboles. So before I start showing you some of the spectra we collected and discuss the result, I want to again start off with a little bit of motivation and give you some background information why we focus on volcanic amphiboles. So it has been recognized for a while that magmas erupting in subduction zones are generally more oxidized compared to magmas erupting in other tectonic settings, such as, for example, mid-ocean ridges. So this is illustrated here on the left, where you can see ferric over total iron ratios of subduction zone magmas in red, and they're contrasted against ferric overtone ratios of magmas erupting in mid-ocean ridges. So you can see that they are generally more oxidized. So one of the motivation of my research is to find out why that is, what are the processes that cause the oxidized nature of subduction zone magmas. But in order to test some of the hypotheses which are out there, we really need a good tracer of melt ferric overtone ratio or of melt oxidation state. And the idea we had was thinking about amphibole, because it's such a common mineral in subduction zone magmas, to develop as such a potential tracer. And the approach we took with the study is to compare volcanic amphibole ferric overtone ratio we can measure using synchrotron Mossbauer spectroscopy and compare them with each other from localities which record a relatively wide range of magmatic oxygen fugacities. And then we can see whether there is a correlation of the ferric overtone ratio in the amphibole we can analyze and sort of the redox state of the magma from which they crystallized. So we focused on 4 active volcanic systems. Those are shown here in a global map. So among those are the Sitacoharo Volcanic Center in central Mexico, the famous 1991 eruption of Mount Pinatubo in the Philippines, and then 2 locations from the United States. Those are the Lassen Magmatic Center in Northern California and the Long Valley Caldera in Central California. So all of those locations erupted amphiboles, so we can take them and analyze them for the major element composition, which allows us to determine their crystallization and pressures in the crust. And that's what you can see here on the right side. So you can see that with an uncertainty, the amphiboles from all of those 4 localities crystallize on very similar pressures and temperatures in the crust. So the questions we can now address to those 4 localities is, do the amphibole ferric overtone ratios reflect primarily crystallization conditions? So do they reflect sort of the conditions they encountered while crystallizing from an oxidized or reduced magma? Or are there any processes which happen after crystallization of the amphibole which potentially modifies the ferric overtone ratios? And if we show that we're actually looking at magmatic ferric overtone ratios, we can then pose the question whether those ratios correlate with ferric overtone ratios in the melt. So the first step we did is to look at the study locations and determine the magmatic oxygen fugacity of the melt. So that basically means how oxidized or reduced were the magmas which crystallized amphiboles. And we can determine that by using different tools. One of the tools we used is looking at iron titanium oxide pairs. On the right, you can see a backscatter electron image of magnetite and ilmenite pair. So you can use their composition to determine the magmatic oxygen fugacity. Another tool we used, which was actually developed by one of my co-authors, is but looking at the iron content of a mineral called biotite. It usually co-crystallizes with amphibole in those magmas. And you can see a microscope image here on the bottom where a brown biotite is fully enclosed in an amphibole. So there's good evidence that they actually co-crystallized. So by using those tools and also combining them with published values, we come up with the diagram here in the middle, which shows you that magmas erupting at Lassen and Mount Pinatubo are relatively oxidized. And then on the reduced end, we have magmas erupting at the Long Valley caldera. And magmas at Sitakara are sort of in between those two end members. So we have a relatively wide range of magmatic oxygen fugacities within those four localities. So now the important part really is to figure out whether the ferric overtone ratios we can analyze represent magmatic conditions or if they have been modified after crystallization. And in order to do that, we can look at the water content and the hydrogen isotope composition of the amphiboles. And the reason why those two parameters are helpful in answering this question is because there are two processes which are capable of modifying amphibole chemistry after crystallization. And these are dehydrogenation and dehydration. So on the right side here, you can see that the process of dehydrogenation, which is basically the release of hydrogen from the amphibole structure, causes a decrease of the water content in amphibole, but at the same time also a trend towards heavier, higher hydrogen isotope composition. So in the formula, you can also see here on the right, dehydrogenation is associated with the oxidation of ferrous to ferric iron. So that's really important for us. We need to figure out whether dehydrogenation has impacted those amphiboles. And then the second process is dehydration, which is the release of water from the structure. It's also associated with a decrease of the water content in amphibole, but it creates a trend towards lighter or lower delta D hydrogen isotope compositions. So we can now plot our data in the water delta D space, which is on the left. And you can see right away that the majority of amphibole compositions basically plot in a relatively narrow field, around 1.58% water and negative 80 per mole. Exceptions to these are some amphiboles from Lassen and the Long Valley caldera, which show this trend towards lower water contents and heavier hydrogen isotope compositions. So one concern we had at the beginning is that potentially beam-induced dehydration is something which could lower the water content in the amphiboles or potentially oxidize the iron. So in order to test that, we analyzed the water contents in individual amphiboles prior to exposure to synchrotron radiation and after. So this is shown here at the right, where we again look at the exactly same grain and their water content before exposure and after exposure. And there's no difference within uncertainty, so we're quite comfortable saying that the low water contents and the heavy hydrogen isotope composition we see in some of the amphiboles from Lassen and Long Valley actually due to post-crystallization dehydrogenation. So let's zoom into the data a little bit more and look at individual grains. So those are two grains, those are backscatter electron images of two grains from Long Valley. And you can see that within those two grains, there are larger, big differences, intergrain compositional heterogeneities in water and hydrogen isotope composition. So within a distance of 100 to 200 microns, we can see differences in water content of 0.28% and difference in hydrogen isotope composition of about 200 per mil. And that's quite astonishing. That was quite unexpected. And that highlights again the necessity for high spatial resolution methods, and also implies that there are potential differences in ferric over tau ratio in individual grains on a relatively small spatial scale. So now we figured out that some grains from Lassen and Long Valley potentially experience dehydrogenation and associate with that oxidation of iron after crystallization from a magma. But how do we know that the majority of grains which plot in this narrow range are actually representing magmatic conditions? And that can be evaluated if we compare amphibole hydrogen isotope composition to the hydrogen isotope composition of melt inclusions, which basically directly reflect the composition of the magma. And this is shown here. So those are a couple published studies looking into the hydrogen isotope composition of typical subduction zone magmas. And you can see that the majority of amphiboles actually overlap with those estimates. So we think that they really represent magmatic conditions and have not been modified after crystallization. And we can model a dehydrogenation and dehydration processes by using a simple Rayleigh fractionation model. So this is indicated here on the left by the yellow and purple lines. So we choose slightly different starting composition for Lassen and Long Valley because they crystallize from compositionally different magmas. And I have to point out that fractionation factors are not very well constrained experimentally. But if you take what is published out there, you can basically come up with what is shown on the left. And what that means is that we can only recreate the full range of values by a combination of dehydration and dehydrogenation. So this is illustrated by the gray arrows here. So what that means in sort of a geological context is that we think that dehydrogenation is happening to the amphiboles after crystallization in the magma reservoir, but prior to eruption, probably during heating of incoming Mojado magma. And then once they're mobilized and they're sent towards the surface and erupt, they experience dehydrogenation. So it's a combination of both processes. Okay, let's have a look at some of the results. Some of the spectra we collected using single crystal mass spectroscopy, beamline 3. So let's start off by looking at an example of a dehydrogenated grain. So this is a grain from Lassen, which has lower water contents and heavier hydrogen isotope composition. And we collected spectra in 24 bunch mode and hybrid mode along different crystallographic orientations. And we were able to find a model, a chemical model for this one crystal fitting all of the different spectra collected along different orientations. And we came up with a ferric overtone ratio, which is rather high, 0.86, but it really fits our assumption that this is a grain which has experienced dehydrogenation and post-crystallization oxidation. And it also fits well with the observation we can see in the microscope, which is that a lot of grains in the sample actually show this red coloring, which is indicative of iron oxidation. And next, let's have a look at two grains we think have not experienced any post-crystallization modification, but really represent magmatic values. So this is a grain from Mount Pinatubo and another grain from the Long Valley caldera. And remember, Mount Pinatubo is this location which erupted really oxidized magmas, versus the Long Valley is at the other end of our spectra, a magma which was relatively reduced. So now when we, again, collect spectra, find a model, and get ferric overtone ratios, we can see that the Mount Pinatubo amphibole records a relatively high ferric overtone ratio of 0.62, versus the Long Valley amphibole records a relatively low ferric overtone ratio of 0.14. So this fits with our initial assumption that amphibole ferric overtone ratios are actually correlating with the oxidation state of the magma from which they crystallized. Okay, so providing you with some summary and conclusions. So by using synchrotron mass spectroscopy and combining different setups, we're able to determine ferric overtone ratios in volcanic amphiboles, which range between 0.14 and 0.89, so relatively wide range. And as a first result, we showed that amphibole ferric overtone ratio increased with the magmatic oxygen fugacity of the host magmas. And then also by correlating textures we see in the microscope, water contents, hydrogen isotope compositions, and ferric overtone ratios, we showed that some amphiboles experience dehydrogenation and possibly dehydration, where other amphiboles really reflect magmatic conditions. So one of the major outcomes of the study is that it's absolutely essential to evaluate whether the Figure-tone ratios are primary or have been modified after crystallization prior to any interpretation. And then last, the combination of high spatial resolution methods is really powerful if you want to correlate those individual data sets and avoid analyzing inclusions which are present in natural amphiboles and avoid averaging across compositional heterogeneities. Okay, thank you so much. I'm happy to answer any questions.
Wonderful. Thank you for taking us to this geological journey. We might have time for one quick question. I think you can mute yourself and ask a question. If not, let's postpone questions to the end of the session. And let's move on to the next speaker. Is Jennifer Jackson from Caltech as well. She's going to take us to a journey to the center of the Earth. Please take it away, Jennifer.
Thank you. Can you hear me okay?
Is perfect. Yes.
And you see my screen?
It's perfect.
Okay, great. Thank you. So I'd first like to begin by thanking the organizers for the opportunity to share this research on Earth's deep interior. And this image on the right here is a snapshot of an evolved geologic structure in peach colors. And it is perched on top of Earth's core mantle boundary. And the temperature of this boundary is really controlled by the temperature of Earth's core, which affects many phenomena, in particular the phase relations at this boundary, including ultra-low velocity zones, which are small patches, small enigmatic structures that are perched on top of Earth's core mantle boundary and dispersed about the entire planet. And these are the two topics that I will cover today in my talk. But before we get started, I would like to thank my current and former group members, including Bob Sirachbacher, who gave the previous talk. And in this talk today, it's really going to focus on the melting curve of an iron-nickel silicon alloy, which was the topic of Vasily Dobrosavyevic's PhD. He is now a postdoctoral fellow at Carnegie. I will also highlight some work that both he and Boon Lai did together. Boon Lai is a seismologist. She is Australia National University. And current PhD student, Sijin Zhe. And I would also like to thank all of our colleagues and collaborators at the Advanced Photon Source, Sectors 3 and 30, Sector 13, GSE CARS, and HP-CAT for their help and collaboration with all the experiments that and the results that I'm going to present today. And I also like to thank the National Science Foundation and other funding sources for supporting this work. Okay, so over the last several centuries, many scientists have contributed to our understanding of Earth's deep interior. And in a seminal paper, actually, in 1936, Inga Lehman, simple model of Earth's core could not explain the arrival of seismic core phases, concluding that there must be a solid inner core nestled within a liquid outer core. That is, she discovered the deepest thermometer inside of Earth. And since then, high-pressure physicists and earth scientists have sought to constrain the solidus of Earth's core, which would then define the temperature in that region. And the temperature of Earth's core affects many phenomena. It affects us, like I was showing in the first slide, it affects structures that are perched on top of Earth's core mantle boundary. These are multi-scale structures. This is a highly schematic cross-section of Earth's deep interior. One of these structures I'm going to focus on are these ultra-low velocity zones. And these ultra-low velocity zones in some areas around the planet have been thought to be connected to mantle upwellings. And these mantle upwellings combined with subduction help really drive the circulation of the mantle. And one of these upwellings includes the deep-seated upwelling that's underneath the Pacific plate that may be feeding the material in a complex magma system beneath Hawaii. And so therefore, the temperature of the core really plays an important role in controlling many of these complex phenomena and processes from our mantle base to the surface of the planet. So in the talk today, I'm going to first focus on the temperature of the core mantle boundary. We're going to approach that from the core side. And it's also going to highlight a dual technique approach, an approach that accesses different time and length scales of the involved spatial temporal arrangements. As the temperature of the Earth's core influences many phenomena, the second part of the talk will focus on these small enigmatic structures, ultra-low velocity zones, which will also rely in part on inelastic X-ray scattering measurements. Okay, so turning first to the thermal constraints of Earth's core, here we show a phase diagram of iron, an iron alloyed with 10% nickel. The solidus or melting of core-forming alloys at the boundary between Earth's solid core and liquid core thus determines the core temperatures. So it is known that there should be light elements in Earth's core due to the density deficit observed geophysically between that of an iron nickel alloy and that again of the geophysical constraints. And the again going back into the rationale for understanding the temperature of the Earth core is it affects the heat flow through the core mantle boundary and influences these dynamics and controls the phase relations in these mantle structures. But then turning back to the light element. So as the geophysical constraints show that there should be some amount of light elements in Earth's core. However, light elements, their effects are poorly understood, and different techniques have really shown large discrepancies. And so our approach is a dual technique approach that investigates an iron nickel silicon alloy. So we're investigating the effect of silicon on the melting phase relations of an iron nickel alloy using two independent in situ techniques that accesses different time and length scales of the involved spatiotemporal atomic arrangements. And that is, we are using synchrotron Moosbauer spectroscopy, which probes the dynamics of the iron 57 nuclei with negligible background. And synchrotron X-ray diffraction detects liquid diffuse scattering signals, constrains the subsolidus phase relations, and tracks in situ thermal pressure during heating. Here is an array of pictures from many of the experiments that we've been conducting. So all melting experiments that are shown here today were conducted at the Advanced Photon Source at two different beamlines. The Moosbauer spectroscopy measurements were conducted at 3 IDB, and the X-ray diffraction experiments were conducted at GSE CARS 13 IDDD. Shown here is a typical sample loading environment of the sample surrounded by a potassium chloride thermal insulator, as well as a fleet of diamond anvil cells that we typically take to conduct these experiments. So in the SMS experiments, the incident photons with an energy of 14.4 keV interact with the iron 57 atoms in the sample. And the time-delayed photons are produced exclusively by the excitation of solid-bound iron nuclei. A fit to the time spectrum constrains the sample thickness, among other properties. And during the melting run, we integrate the time-delayed photons over this shown time window, so as to conduct the experiments as fast as possible. So the Moosbauer signal can be understood in terms of the Lamb-Moosbauer factor. This is named in part by Lamb, who studied this phenomena using neutrons in the 1930s, and Moosbauer, who discovered the Moosbauer effect. So it's related to the probing wave vector and the mean square displacement, and sensitive to the dynamics of the atoms. It distinguishes a liquid from an amorphous state. It was demonstrated for tin at ambient pressure. And using time domain, Moosbauer spectroscopy, we take advantage of the highly prized quantities of synchrotron radiation, that is collimation, selectivity, and sensitivity. This technique was demonstrated by iron and also demonstrated for an iron-nickel alloy by Dongjia Zheng as part of his PhD thesis. And now we're going to describe our constraints on an iron-nickel silicon alloy. So I also want to point out that this scattering intensity model is used to fit the data, and that considers several physical aspects of the experiment and the samples: sample thickness, laser hotspot size, X-ray spot size and shape. And in doing so, really constrains the first onset of melting. Okay, now we turn to the X-ray diffraction experiments. So in these X-ray diffraction experiments, we conduct these at GSE cars using an automated burst heating method that they have developed, collecting first a hot pattern followed by a cold pattern. Here it shows a temperature sequence that we put together. In the scattering process of diffraction, of course, everything with an appropriate scattering cross-section and the focal volume contributes to the measured signal. And typical analysis of trying to detect a signal from a melt from such a suite of patterns involves trying to detect a often subtle signal that must rise above all of these other scattering contributions, essentially trying to detect a change in the shape of a background of the signal. And so this can create some challenges because noisy fluctuations in the reference background can often mask small liquid diffuse scattering signals and may lead to an overestimated melting temperature. And so what we do is that we update the reference background with using the burst heating mode corresponding with a corresponding cold XRD pattern. And in doing so, we can see that there's a clear indication now of where that signal is starting to rise above the background. And it becomes much more obvious. And so using these two techniques, two independent techniques, we populate the phase diagram of this iron-nickel silicon alloy. and finding excellent agreement between these two independent techniques, concluding that 10 mole % silicon, which is a typical concentration of silicon that is invoked for the composition of Earth's core, reduces melting temperatures of an iron nickel alloy by about 250 degrees at relatively low pressures, i.e. the planet Mercury, and up to about 500 Kelvin at Earth's outer core pressures. This would imply a temperature of the core mantle boundary around 3,500 Kelvin. And so as the temperature of the core influences the structures that are perched above it, we will now turn to the topic of investigating some of these small structures and trying to figure out what they're made out of. So this temperature is a relatively cool temperature. So we'll now turn to the last part of my talk, where we're looking at ultra-low velocity zones at the core mantle boundary. And skipping over some of the several decades-long research in identifying these structures using seismic waveforms, from many of these studies, we can briefly summarize what they are. That the seismic waveform studies, they've constrained extreme velocity reductions. Shear waves have been shown to be depressed by up to 50% relative to the mantle surrounding it, with thickness estimates ranging from a few kilometers to about 80 kilometers or so. So just, a few references here. Mount Everest is 8.8 kilometers. High Mauna Kea rises 9.2 kilometers. Olympus Mons at 25 kilometers. So these are the types of scales of these features. So they're actually not that small. So these structures could be harboring ancient materials that have been isolated from the mantle over the billion years of its convective cycle. Just the origin is really not that well known. And the studies that have tried to approach this have usually there's been an absence of experimental constraints and quantitative evaluation in terms of geophysical observations that are used to interpret these structures. And so just in a little bit more detail, we can see this wide range of velocity reductions that explain a plethora of ultra-low velocity zones that are perched on top of the core mantle boundary. So we see shear wave reductions and here, say P wave reductions on the vertical axis and S wave reductions on the horizontal axis, and S wave reductions by about 50%. And some of these ratios include this nominal 3:1 ratio, which has often been invoked as a partial melt hypothesis. But in many of these studies, this ratio is fixed in the seismic analyses, usually measuring one phase or another, the P wave or the S wave, rarely both. And so we're going to hypothesize what these ultra-low velocity zones could be made out of. And so from iron partitioning studies that have investigated coexisting silicates with oxides, it shows that iron strongly prefers the oxide. So this led me to hypothesize that some of these ultra-low velocity zones could contain an iron-rich oxide. Magnesiowustite is very dense, therefore it could explain some of these PCP studies. It's also could be stable over billions of years. And so to test this hypothesis, We've measured nuclear resonant inelastic X-ray scattering spectra and high energy resolution inelastic X-ray scattering on polycrystals and single crystals. Analysis of these measurements, these form the basis of former PhD student June Wicks, showed extreme velocity reductions. That iron-rich MgFeO or iron-rich magnesiowustite has ultra-low velocities and is also highly anisotropic under extreme pressures. And so now we can look at a case study underneath present-day Hawaii. This is a seismic study that was led by former PhD student Boon Lai. She worked together with Vasilier to create synthetic models of seismic waveforms from deep Fiji events. And they performed a best fit minimization to interpret the mineralogy of these ultra-low velocity zones that were sampled in this particular seismic study. And what we show here in the next slide is the S-wave reduction as a function of density for different mineralogical assemblages that bear this iron-rich magnesiowustite sample. The reason for the two different curves for each of these mixings, so we mix the silicate and the calcium silicate phase of the mantle, is due to the uncertainties in how those grains are basically interlocking, if they're in uniform stress or a uniform strain environment. So a Royce bound or a Voigt bound. And here is the 30-kilometer model that was favored in our seismic studies for the height of this ultra-low velocity zones. The question is, once we determine the amount of magnesiowustite in this assemblage, the question is, are these too dense to actually rise up to 30 kilometers? If the assemblage is too dense, it's just going to flatten out like a pancake over geologic time. And so we collaborated with geodynamicists and rheologists to constrain the viscosity and also the heights of expected assemblages that could bear this iron-rich magnesium oxide. And we see that they do indeed fall within a reasonable bound for structures that could rise up to about 30 kilometers. These values here are just the initial starting thickness of a geodynamic model that incorporates this chemically distinct structure. Okay, so in conclusion, a pair of independent in situ techniques that access the different time and length scales of the involved spatiotemporal atomic arrangements can precisely constrain melting and the phase relations of terrestrial core materials. In particular, we studied iron-nickel silicon alloy, showing that temperatures of the core could be reduced such that the temperature at the core mantle boundary could be about 3,500 Kelvin. This would influence the phase relations at Earth's mantle base, which also influences the dynamics of this region. And so looking forward, high studies in elasticity studies will benefit significantly from the APS upgrade. We can routinely achieve pressures above 1 megabar. Melt detection becomes obvious with a reduced X-ray focus spot size. This is a simulation I did for one of the melting runs. And we could fully realize the potential of a dual in situ technique measurement for phase relations and melting. And with that, I thank you, and I'm happy to turn it back to you, Barbara.
Great. Thank you, Jennifer. That was a wonderful presentation. And we also really thank you for, being so committed to very difficult and challenging and hard experiments to conduct. So Then I would invite with this Ertin and Gian to pitch in, and to anyone in the audience to pose a question.
Thank you, Barbara. First, I will give a chance for the audience to ask their questions. Anyone has any question to any of the speakers?
Yeah, I have a question about the plans for the undulators after the upgrade. There's a Gatling gun version, and then there's kind of a sliding version. Are both of them planned, or what's the understanding of what undulator would be used for sector 3?
Right now we have a single undulator, two undulators in the 27 millimeter the size. So that will cover both 14 keV and between 20 and 30 keV. So that will cover the 14 keV, use the third harmonic. So the flux will be double compared with right now. But the cost is the heat load. It's not first harmonic. It's not optimized. It's not the best condition we are hoping.
So it's basically the two that are above and below each other and moved in and out. Is that right?
Well, that is the revolver we call. So once if we can get that one, so basically so the new one, the newest type is up and down, two types. You can move it up and down to change between 18 and 25 millimeter, two devices to optimize for different energy range.
And it's something we're hoping for.
It's not in the plan yet. So we have to work towards that. The undulator is the major thing we can get from the APS-U. Well, as you know, APS-U is right now they split the $800 million between the accelerator and the beamline. So beamline, we don't get much of the support yet. So, but there's a phase 2, phase 3, as you know, for the Brookhaven, for the older storage drain, it's like this. So hopefully we can get something later on and then optimize that the beamline and the insertion device for our program. So the first phase, the undulator is not in there.
Any other question? So I have a couple of questions. I'll start with Volker, and then if Nikolai Leonard is still with us, but I don't see his name. And then I have one question to Brent. Please stay online, Brent. So Volker, can you hear me?
Yes.
Excellent. Thanks for staying on.
What is
We can hear you.
Yeah. Okay.
So
great.
you showed this beautiful wheel structure with dysprosium and iron on top of each other, and with a strange magnetism. Can you tell a little bit more about what do you hope to learn from that?
I wanted to see whether we can get any information about the ordering, the toroidal ordering of the dysprosium by NFS and also by conventional mass power spectroscopy on the iron side. It actually that started by measuring an iron 19 wheel, which is has a completely different behavior. It's super paramagnetic, and it's just a very nice molecule, and it has this new feature, the toroidal moment, that I wanted to employ.
Has this been studied or synthesized, or?
That has been synthesized by the Powell group and it was published. I think that's Jack's communication in Jack's work in 2020.
But not enriched.
You mean in
iron or dysprosium?
In iron? No, we have that in iron 57. We measured it at Petra.
Oh, okay.
Mm-hmm.
So this is something going on at the moment.
Yeah, exactly. I wanted to show some results from the last beam time. This is the complex, one of the complexes we measured in September.
Okay. I have a question to Brent. Are you there, Brent? You probably are.
Yes, I'm here.
Ah, excellent. You showed this, what you called crazy behavior around the Curie temperature, where you compare the XMCD data to NFS data, and the scatter on the XMCD data was horrible. So can you comment on that a little bit?
Not really, but I can say that some of them got better with the later references. The first ones were pretty poor. I don't know what the technique improvements were. It's out of my area.
So if you compare the two, can you reconcile the results?
The magnetic circular dichroism magnetization, you're saying, how does it compare to ours? Some of them aren't bad. There's one of them that's pretty close, but it probably, I haven't thought about whether there could be some short range order that it's possible to see with the X-ray method. If so, there might be some short range correlations in the spin orientations that they're picking up that we are not. It's possible, but there's such a scatter in that. I'm not really sure if I believe it.
Okay. Is Nikolai Leonard with us, or he's gone?
I don't think so.
I don't see him. Yeah, I don't have any other question.
Well, I was curious for Brent Foltz again about hydrostaticity, if there's any chance that that is an issue, and if it's also a challenge to do some measurements with a small sample condition required for hydrostatic conditions to be maintained.
Well, let me try to remember. The pressure medium was an inert gas. We were pretty low in pressure. So I really don't worry about that too much in this case. The idea was first to see a result. If there are variations locally in the pressure, it could be responsible for some of the problems we were having right near the Curie pressure. We do know that there were relaxations in time in the pressure cell, and the pressure evolved over maybe 20 minutes, 30 minutes or so. And it could have been causing some difficulties right there because there's such a sensitivity of the physical properties to the pressure near the Curie transition. So I think that might be the bigger problem right now than the, shall we say, distributions of pressures, time stability of pressures. The hydrostatic part, though, with was it neon? It was inert gas anyway. So I don't think that's as big a problem. So.
Great, thank you.
Can I ask a question to Jennifer? Hi, Jennifer.
Hello, Arjun.
Yesterday, there was a session where there were a review kind of perspectives on APS and APS-U, and Russ Hamley mentioned one of the grand challenges as the melting point of iron, still not completely understood. Where do you think the limits will be when the APS-U come back, that you will be able to push the temperature and the pressure range?
Well, I think with the smaller X-ray focus spot size, we can certainly pursue much higher pressures, but the essential part is having agreement between different techniques that access these different time and lengths. because otherwise, one could do a measurement with one technique at ultra high pressure and then another measurement at ultra high pressure. And as the detection strategy may be different or not optimized, it could still, report a wide range of results.
How about the temperature measurements when you go from 13 to sector 3? Do they agree? I mean, is there an understanding? They are the same methods to measure the temperature, at least?
Similar, but at sector 3, when we use the faster system that we developed with, during Deng Zhao's PhD thesis, that was clearly precise, right? So there are, up to 300 hertz. So we can collect many measurement points per, each, let's say 3-second integration time for the SMS spectrum. And what we showed, with the iron nickel silicon study was excellent agreement. But the high precision and temperature measurements using something like a PM, a suite of PMTs. It's an array. It's basically an array spectrometer that selects out those 5 wavelengths. So it acts like a CCD. But these fast temperature measurements with any type of fast CCD and combining 2 techniques, I think is going to be absolutely essential.
So when we move the station from B to C station, the high pressure setup, do you have plans to change the laser heating system, updated, or what is your preference? What is your wish list for upgrade of the high temperature system?
Well, the wish list is to up some of the optics. We're still discussing this with Jiyoung, and there's certainly benefits to a redesign, which also requires funding for that. But it certainly
how much
will benefit.
How much do you need, estimate-wise?
It ranges from a few $100K to probably about as several $100K. So depending on, just depending on how much and how detailed we want to upgrade.
Is there a model in your mind, like at another synchrotron or at another beamline? Do you have a?
Well, I see Vitali is on the line and Deng Zhao has his hand up. GSE car system is a well-oiled machine.
Okay.
So that is, that's a system that if it can be integrated into the C station, that's the dream model as of now. But Vitali has his hand up and Deng Zhao has his hand up. So.
So let's have Deng Zhao asking question first.
Anybody wants to say something? Deng Zhao or Vitali?
Deng Zhao is unmuted.
Vitali?
Yeah, Deng Zhao is trying to fix his microphone, I think.
So can you hear me now?
Yes.
Okay. Yeah. So I have a little bit of comment regarding this. I think the for now, I think the JC Car's Vitali system is pretty good. It's a very great model to copy to if sector 3 do have the space and have the funding support to update that. Yeah. So basically, the faster system is definitely great when we use it, but it's already 10 years old. Yeah, let's be real with that. But now it was designed because the CCD system to raise the temperature at laser heating was as fast as only 2 hertz. at most, I guess. But now the CCD spectrometer has already developed quite a lot, and I believe with Vitali system there can be already like a CCD system with integration time of 5 milliseconds, which means that's 200 hertz at least. Yeah, and this can be shutterless, so we don't need to use a mechanical shutter. And I mean, with that purpose, I mean, it provides spectroscopy wise, it provides a much better resolution and should be more robust temperature fitting than the faster system. But on the other hand, I think the faster system can even go even faster because previously faster system was limited by the temperature reading speed was limited by the epochs, which I believe based on what Mark told me, it was 2 kilohertz. But because Sector 3 has already a very fancy nanosecond resolution of timing system, I was hoping that actually the PMT array has the capability to go to nanosecond resolution in temperature reading. So that's another possibility that we can upgrade the faster system as well. Yeah. And technically, I do have a question. Yeah, very technical question. So in the past, I mean, Sector 3 has had to put the 2 laser system on top of the hatch in IDB station. If you move the laser system to IDC, will that be a problem? Because I remember it was due to some temperature and also stability issue for the monochromator. So if you move the whole laser heating system to IDC, do you think it's possible to leave the laser inside the hatch, or do we have to put the laser module on top of the hatch again? I'm asking this question because I think IDC is a much taller, much higher station, and it will be very difficult for the optical fiber to reach the optical table if you choose to do that.
It will not be a problem because the B station, you have high resolution mono optics in there. For C station, we don't have that condition. Additional to that, so what our plan is to put the fiber laser and the module inside, but the laser heat, the water cooling units outside of the station. So there will be no effect. Just like similar to what JC Cars is doing.
But I think Vitali is leaving the laser whole module inside the hatch.
The module is technically inside.
It's a water cooled, so it doesn't matter.
That's right.
It's not air
the
cooled.
module
so,
is water cooled, doesn't produce lots of heat.
Yeah.
The cooling module, the circulator producing heat, it can be outside.
Okay.
Yeah, for the cooling. I think I'm not sure, Jiang, we probably should tell that right now we're redesigning the entire laser heating system, so it will be much larger optical table, and we will make sure that all our systems are very compatible, and in the future we'll use probably the same calibration lamp for temperature measurements, similar detector, spectrometer, so it will be very reproducible data collection.
Yeah.
So we are working on it. So I think in 1 year it will be base system, and
basically Vitali and I are discussing and working towards the same system to deploy it at both stations. And I think Jenny's plan is doing the laser heating and melting continue. The thing is, the condition is we have to get the 48 bunch mode to do that. And also to incorporate all the advance of the technology of the laser and also temperature reading technology. So that will take a little time, but that's in the plan.
Right.
Coming back to Jennifer, along the lines of grand challenges, do you think measuring iron is enough, or do you really want to go to iron alloys?
Yeah, definitely, because so I didn't have time to go into all of the previous measurements of iron, nickel, silicon alloys, but from the wide range of techniques that have been used, there is an equally wide discrepancy. They are all over the map in terms of whether they, for similar concentrations, as to whether they have a melting point than iron or a lower melting point than iron. They're solidest, to be accurate.
Just to add, Jennifer, there are new data existing right now for the iron, and it's not simple phase diagram that it's only HCP above 130 GPa. So it's definitely room to improve our data collection, and we still need measurements of magnetic properties of iron.
Exactly.
There is still BCC iron, and we can confirm that with XFEL facilities, but yeah. You will be busy, don't worry.
Absolutely. Yes.
So does
Okay,
it
so
make
along
sense,
this line,
Jennifer?
sorry, I have a question following the question about the melting. So just maybe just a clarifying for me, do you think actually if you can do X-ray diffraction and the forward scattering really at the same time on the same sample in the same beam time, you think will that resolve some of the issues?
Absolutely.
Right, but is that
But
possible?
the quality of the measured data, needs to approach that of doing the two measurements independently. So it's a matter of having enough flux in the same time period that we could collect a statistically significant amount of counts, for example, and get the right statistical quality of an X-ray diffraction pattern, because in that pattern, right, we have to search in the weeds for the subtle liquid diffuse scattering signal. And so it really matters how much data collection time for.
Is that even in the upgrade, is still going to be true? Is that actually nuclear forward scattering will take a little bit longer to collect at each sort of temperature point? I mean, diffraction is much faster. Is that true? Or
It really depends on what one is.
The quality of data, of course.
Well, it depends on the bandwidth of the X-rays too.
Yeah,
right?
exactly.
And the current in the ring. So
yeah, technically in the past,
is milli EV beam enough, strong enough to get comparable results to 13 IDD, or do you really need EV beam?
Really need an
also different photon energy also.
Yeah,
right?
yeah, but they're definitely creative. One could try to do this, I think.
But you guys already get a very
But
fancy
even let's
error
say,
detector.
how about this polarized analyzer? Because in principle, I don't know. Yeah, there's a technical issue. Do you use EV beam or milli EV beam, and then how do right?
Yeah, thank you, Jennifer. Your challenge will remain for maybe APS-U 3 or APS-U 4. Anybody else? Any question? Any comments? Any remarks? Walker,
well,
what do you
just
want
as I was
from us?
talking
Yeah.
during my presentation, we got news that Nature Physics has accepted the INVAR manuscript. So we'll go with
congratulations.
322 days of review. And my favorite review comment was that I calculated the required force to get these high pressures on such a small sample, and I find it's only hundreds of newtons. A high school child should be able to produce such pressures. Why is this an important experimental technique?
Yeah, why did you find what you find at low pressure? You have to find it at high pressure. Walker, what do you want from us?
I have a question, not only concerning dysprosium, but also concerning iron. After the upgrade, will it be easier to measure thin layers?
You mean grazing incidence?
Grazing incidence, yeah.
The beam is
for
smaller.
example, yeah, but the beam is smaller. But I don't want to measure single objects, but for example, coated surface, coated with, for example, iron molecules or coated with even dysprosium molecules.
Well, you don't have to use horizontal focusing. You can make it beam pretty wide and focus only in one direction. So you can get a swath of beam on a larger area.
Yeah, and but with respect to intensity, to flux, will it be more after the upgrade than now?
At 25 or at 14? Which one are you?
Both 25 and 14. But
Yeah, I mean,
for
flux will
grazing,
be, I think it's already going to be a factor of 2 because of the increased current.
Mhm.
But for dysprosium, the situation improves significantly because the 48 bunch modes is still suitable for your work. But for iron, we have to think some another way. So
Okay.
yeah.
Mm-hmm. Okay, thank you.
Well, for the flux wise, I mean we double the current, but due to the lower energy of electron beam and the angulators, so that actually the actual gain in flux as current as what we have, I mean in terms of all the optics, it won't be, it won't be double. It'd be like I don't know. Tom must have the better numbers, like 20%, 15, 20%. But with the newer, if we do get the newer high-resolution monochromator, is in vacuum, the efficiency, maybe even higher.
I think for dysprosium, the important thing is to get a detector with a 0.1 nanosecond resolution.
Mm-hmm.
And
Yeah.
possibly higher, like a thicker diode,
Thicker
higher.
diode and faster.
But then that go against the
asking
energy
too much.
resolution. So I mean the time resolution. So yeah, it's a tough.
Yeah.
But maybe with the detector configuration or uses
Well,
multi-element.
Yeah,
maybe.
smaller pixel size helps. So if we can
Yeah.
get thick silicon with a millimeter size detector, it might actually work out fine. But that will give you more sensitivity on the hyperfine fields. Okay, Barbara, do we have anything else?
Can you hear me? Yeah.
Almost.
Actually, Donjo is asking.
Go ahead, Donjo.
Yeah, I have one quick question for the success rate staffs. So I'm just curious, based on the talks that I listened to this morning, it seems that there are only 50% time will be 48 bunch mode, which is timing mode, kind of. And it seems that you're going to put European dysprosium and out toward that direction. So how much time do you envision there will be left for the iron's timing mode? If I want to do some research with iron with timing mode, how much time percentage do you expect?
Actually, the challenge is even worse.
Yeah.
So they say right now it's not 50-50, so it's like 40%. Yeah, and
It would be a miracle to get 48 bunch mode on day one. It will take time.
That's another thing.
They may start with doublets or triplets, which will enable inelastic scattering, but not forward scattering. So iron inelastic scattering probably will continue sooner, and forward scattering will follow, but it will take time.
Okay.
Is it known whether they would prefer doublets or triplets at this point if they do that?
Well, even the doublets are not exactly doublets because they cannot put immediately. They have to leave 2 buckets free and then put on the 3rd bucket. So they are like 10, 12 nanoseconds apart. But since it's an unknown baby, we don't know how it's going to be born. So let's just hope for the best so that the sooner they can get to 48 singlets, the better. But initially, the emphasis is on storing 25 milliamp and finishing the project on time and on budget.
Yeah. So I don't want to get anybody hopes up, but the current plan is that starting, for example, starting 2024-2, we'll commission the beam lines, all that. So that's summer. And in fall, there will be more confidence, like in the maybe 100 milliamp, 125 milliamp range, 150 milliamp range to start doing timing mode more reliably. But there, the current one in timing mode will be lower. It's like 130. They're comfortable. They're conservative. They're comfortable. They can do that. But looks like timing mode. We can maybe if you're lucky, you can start seeing some in the summer already. More likely in the fall, and go from there. So.
Yeah, and those time will be account for all the NREX experiment. Some of the European and dysprosium timing forward scattering, and maybe a little bit of iron forward scattering.
Well, that will be decided also with, the proposals coming in. It's never been set in stones prior. So we are more concerned with the ability to do all these things. It's going to be shrank. So obviously it's going to become more competitive, but then proposals with scores would compete with time.
I'm not pessimistic. I'm quite optimistic, actually. Things will be okay. Go ahead, Brent.
Is there anything that can be prepared for today regarding the machine operations for clean buckets after each pulse? Does anyone know how to approach this problem?
Bunch cleaning is a sore point because APS opted to go for swap in, swap out type of injection system, which means instead of topping up fraction of a charge, they take the whole bunch and replace it with a new bunch. And so therefore they don't have a fast kicker the way ESRF has to clean up the stray bunches. So bunch purity, especially near the first main bunch, is going to remain as a sore issue because they don't have the fast kicker, because of the way they chose to inject into the ring and take the old bunches out. So we are working with them, but they are not committal because they want to be able to deliver the minimum bare minimums to the DOE is saying that the project is completed.
So there's some risk that it may not be really working well for a while after first light.
That's true.
Yeah, the good thing is I think that there are pressures other than us. For example, the DCM cat, the shock compression people, they're saying they cannot do they cannot do anything in non-timing mode. And also there's also this pump probe experiment.
There are other timing groups, so we're not the only one putting pressure on them. Okay, Jiyoung, do you want to conclude?
Well, thank you, everybody, for the excellent job for the last 25 years with us, and hope the best for the APS-U. And we are still working hard for that. And if you have any idea, any question, contact with us, and we can communicate through the email. And we have a CONUS workshop coming next month in May. I think every one of you here already received those and sent some students here. So we will have a CONUS workshop in May on the May 10th to 12th. And Wolfgang modified his program, so we will show how to analyze the future data with this CONUS and for the hardware, the new spectrometer Tom is working on. So if you are interested to check in, and we'll start from there.
Thank you.
With that,
thank you, everyone.
Bye, everybody.
Bye.
Long session.
Okay.
Thank you very much.
Thank you, Walker. Thank you, everybody.
Okay, I will stop
Thank
recording
you.
now.
Yeah. Thank you and see you.